Hey, this is a short but very important lecture. Machine learning can be performed in many programming languages. We have chosen Python for several reasons, all of which we will explore in the next lesson. Now, in order to continue with the course, you will need to install Anaconda, Python 3, Jupyter Notebook, and the TensorFlow package. In this section, we will show you how to do that, and we will help you learn about the environment in which we will code. Even if you already have Anaconda, Python 3, and Jupyter installed, this is where we will show you how to install the TensorFlow package. So should you just need the last part, please refer to the last lecture of the section. If you have any technical problems during this section, don't hesitate to ask for our assistance in the Q&A section. Good luck, and thanks for watching. Python and R are probably the two most widely used languages in data science. This course uses Python, and now we will see why. There are actually very few arguments against its usage. It is an open source, general purpose, high-level language. I would like to quickly go over these points. Open source means that it is free to use and people can actually contribute to it. For example, the TensorFlow package for Python that we will use extensively in this course was developed by Google, but was made available to the public for free. If Python wasn't an open source framework, then it wouldn't have happened. Moreover, it is still available for use in all major operating systems: Windows, Mac, and Linux. General purpose shows that it is suitable for all types of needs, not only data science and machine learning, but also pre-processing, web programming, and just about anything you can think of. We will focus on its analytical part. High level. That's a bit more technical, but loosely explained. It has an easy syntax which is close to logical human language, and which is later translated into lower level languages or even ones and zeros. For example, the NumPy package actually goes through the programming language C, and that's why it is so fast. That said, we have to note that Python isn't among the fastest programming languages. However, it is very easy to learn and use, and there are countless packages developed and maintained for it. Okay, now we have to install Python and Jupyter. But why isn't there just one software application called Python that you can just install on your computer that is automatically updated and that runs everything smoothly? Well, Python is a programming language. It can allow you to communicate with the computer. To do that, you'll need the help of a specific software or an application. Namely, the Jupyter Notebook app, which is often called Jupyter, can help us do that. It is a server-client application that allows you to edit your code through a web browser. Consider the following graph. All units represent different software. On one side, you have several language kernels. These are programs designed to read and execute code in a specific programming language, like Python, R, or Julia. The Jupyter installation always comes with an installed Python kernel, and the other kernels can be installed additionally. On the other side, you have various types of interfaces where you can write code. They represent the clients. An example of such a client is the web browser. The Jupyter server provides the environment where a client is matched with a corresponding language's kernel. In our case, we will focus on Python and a web browser as a client or as an interactive shell. Your work will be stored on a notebook document, and since we will be strictly using the Python language, it will be called IPython notebook file with the file format .ipynb. Having said all that, we can explain why Jupyter is used in so many large corporations like Google, Microsoft, and IBM. For its design, it is well suited for demonstrations of programming concepts and training. First, in large corporations, solving a particular task could require coding in a few languages, say Python, R, Julia, or PHP. Instead of installing different interfaces for each language kernel you need, Jupyter allows you to use the same structure of the notebook type of file. Simply, each notebook you create will connect to the language kernel you request. Consider also, this file can be easily stored locally or on a remote server. Therefore, Jupyter facilitates the communication between teams in a corporation tremendously. Second, Jupyter is not a text editor that opens a new window every time you execute a different part of your code, as is the case with some other software applications. In the same file, You can have pure text that can communicate a message to the reader, computer code like Python, and output containing rich text like equations, figures, graphs, pictures, and others. This simplifies the process of workflow immensely, and Jupyter Notebook is increasingly preferred over other software packages. That's why we'll use it too. The next step would be to install Anaconda, a software package that contains both the Python programming language and the Jupyter Notebook app. Thank you for watching. There are various ways to install Python on your computer, but especially for new users, it is highly recommended to opt for Anaconda. It will install not only Python, but also the Jupyter Notebook app and many scientific computing and data science packages. Let's open www.anaconda.com and click on the download button in the home page. You have to pick one of 3 operating systems: Windows, Mac, or Linux. I will show you how to install Anaconda on Windows, but the procedure is identical if you are going to use the Mac or Linux version. Now, you must choose the best among the 4 provided options. Do you need a 2.7 or a 3.6 version? And then there is a 32-bit or a 64-bit version, depending on the Windows you have installed. I know it sounds strange to maintain not 1, but 2 versions of a single program. For this course, the differences between Python 2.7 and 3.6 will be almost insignificant, but we suggest you install 3.6. We will talk more about the differences between the 2 versions later in the course. When you choose between a 32-bit or 64-bit version, you can simply check your operating system. Newer computers are surely running with 64-bit processors, but if you would like to verify this before you begin, you could open your control panel menu from the Start window. Then, select the System and Security icon. Then click on System icon. In my case, it is 64-bit, so when I go back to the Anaconda website, I will select the 64-bit 3.6 Python version. While waiting to complete the download, you can decide whether to leave your email to Anaconda. This is not a necessary step, so you could also select No Thanks and you are good to go. When the download has finished, please double-click on the file to run the application. What follows is nothing different from a standard Windows installer. Agree and press Next until you have the chance to specify a destination folder. You could do this after selecting the Browse button. When satisfied with the indicated directory, click Next one more time. We suggest you pick only the second advanced option. The first option will automate more complicated processes, but causes some problems with previously installed software, while the second will register Anaconda as a default Python on your computer if you have not installed some other package. Finally, click Install and proceed until you see the window where you can finalize the installation. We will not use Anaconda Cloud just yet, and we can learn about the Anaconda support later, so I'll untick both boxes. What you just installed is the whole Anaconda distribution, the Python language, a text editor, many applications and packages. You also have the Jupyter Notebook app. You can open the Start menu and select the respective icon from there. A new window will pop up. It will take a few seconds for the app to load. Once this is done, your web browser will open a new tab with the Jupyter dashboard. In our next video, we'll study the dashboard in more detail and we'll learn how to use Jupyter. See you there. Thanks for watching. Okay, so in this lesson, we'll do a quick tour of the Jupyter dashboard. As soon as you load the notebook, the Jupyter dashboard opens. Each file and directory has a checkbox next to it. By ticking and unticking an item, you can manipulate the respective object. That means you can duplicate or shut down a running file. In addition, you can rename, move, and delete folders. The selection menu allows you to select all the files in the console of the same type by expanding this button. For example, you could mark all the folders or all the running files. In addition, you can check this little box that will directly select all the items on the page. The logic regarding the directory's management is the same as the one of an operation system. Files can be grouped into folders, and folders can contain other folders. From the Upload button in the top right corner, you can upload a notebook in the directory you are in. The standard Explorer box opens, and when you select a file, you can click on Open, and it will immediately appear in your directory. Finally, you can expand the New button. From the list that falls, you will most likely need to create a new text file, a new folder, or a new notebook file. A notebook file can contain code in any of the languages in your notebook section. When you create a new Python notebook file, it will be recorded in the IPython notebook format, .ipynb for brief. Don't fear this other new name, IPython. Think of it as the predecessor of Jupyter. Consider the IPython notebook format as a legacy file format. Alright, let's carry out a few operations. I will rename this folder to Exercises. OK. Done. Now, I will create a new IPython notebook file by expanding the New button and selecting one of the two Python formats I have here. Let's use the default Python format. The browser immediately opens a new tab for me. This is the interactive shell we mentioned earlier. Here, you will write your code and see its output. More on that in our next lecture. Thank you for watching. Okay, great. Now that we know more about the dashboard, we are ready to examine the shell and see how we can code in Jupyter. The field you will see here is called a cell. You can access a cell by pressing Enter. Once you've done that, you'll be able to see the cursor, so you can start typing code. The gray box is called Input field. I will put a short code that says X is a list composed of 4 numbers: 1, 2, 3, and 4. After that, I can ask the computer to print this list for me by typing X. I can execute these commands in 2 ways. The first one is to hold Ctrl and then press Enter. By doing this, the machine will execute the code in the cell, and I will stay there, meaning I will not have created or selected another cell. Observe that an output field with the same number as the input field appeared. Input and output fields of the same number are grouped together. The output represents the machine's response to your commands provided in the corresponding input, and the respective field cannot be modified. The second option allows for a more fluid code writing. To execute the same code, hold Shift and then press Enter. The previous 2 commands are being executed, and then a new cell where you can write code is created. If you use Shift and Enter, you can continue typing code easily. It is amusing that you can cut, copy, and paste cells. You can use the buttons on the main menu. Since we are keen supporters of ergonomics, we suggest you get used to the keyboard shortcuts. When coding, you will mainly have to use the keyboard, so it's worth memorizing different keyboard combinations that would allow you to work faster. Let's see how we can apply shortcuts in practice. I will cut this cell by selecting it, and then pressing the X key. Remember, you can always use the arrow keys to navigate along your notebook file. So, I will move up and then directly press the V key to paste it. My cell was moved up here, below the cell I had selected before I pressed the V key. Now, I will press C to copy the same cell. I will use the same arrow keys again to go down this time. And at the end, I will press V again. Apparently, this cell was copied and pasted below. The other 2 buttons in the menu cannot be substituted by keyboard shortcut combinations. They allow you to move a selected cell up or down, just as I am doing now. Observe that the corresponding output field moves along its input cell. Lovely! Instead of carrying out a command with Shift and Enter, you might prefer clicking on this button with the mouse. The result will be the same. What is interesting is that when you work with more complex code that requires tougher calculations from the computer, While running the code, a little star will appear over here, before the square brackets. Sometimes, this process might take too long to complete. So to stop it or break it, this classical stop symbol can do that for you. 3 other shortcuts could accelerate your coding a lot. Suppose I have selected this cell. After I press the A key, a new empty cell will be inserted above. If I select the same cell and press B, another cell will be created just below. Imagine the last step was a mistake, and I need to delete that empty cell. In this case, it has already been selected, so I can press the D key twice, and it will readily disappear. Wonderful! All the cells we saw so far were code cells. Let's see what is a markdown cell. It is a cell that contains strictly documentation, text not executed as a code. It will contain some message you would like to leave to the reader of the file. To convert a selected cell into a markdown cell, you should either expand this list and opt for markdown, or simply press the M button. Press Enter to access the cell and type some text. When I run this cell, the output will be a simple statement. Now, if you want to turn a markdown cell back to a code cell, select it and opt for code from this drop-down menu. Or press the Y key. To conclude, there are 2 advantages of using Jupyter. First, when your code becomes longer, markdown cells turn out to be useful, as they allow you to leave comments and explain the solution you've created. This is why practitioners love to use them. The other benefit of using this app is you can select and execute whichever cell you want to. You need not run all the previous cells to run a particular cell. This allows for solving a problem in pieces and saves a lot of computation time. This was a long but indispensable lesson. Thank you for watching. Finally, let's look at the libraries we will use in this course. Everyone who uses Python for scientific computing uses NumPy, a third-party package allowing us to work with multi-dimensional arrays. They are a powerful way of organizing and processing data. Hence, NumPy is a fundamental library for those attempting to manipulate larger chunks of information. When your calculations are ready, it is useful to know how to present the results obtained in a graph. Matplotlib is a 2-dimensional plotting library specially designed for visualization of Python and especially NumPy computations. It contains a large set of tools allowing you to customize the appearance of the graphs you are working with. Finally, TensorFlow is the main library we will use for machine learning. While the first coding lectures will rely on NumPy, eventually we will switch to TensorFlow. Okay. The good thing about Anaconda is that NumPy and Matplotlib were installed automatically with it. That's a strong plus of Anaconda. You don't have to install the main packages separately, as you might have to do if you were using some other software for programming in Python. However, TensorFlow is not included in the automatically installed packages, so we will have to do that on our own. That's a useful programming skill to have. So, the quickest way to install it is by going to your Start menu and searching for the Anaconda prompt. Type pip install TensorFlow in the following way. Pip, per se, means either pip install packages or pip installs Python. Strange, but true. Now press Enter. When the operation is done, you will be set up for the whole course. This is one of the quickest and easiest ways to install modules and packages on your computer in general. I recommend you to also pip install Scikit-learn, as you may find it useful in future projects outside the scope of this course. Great! Now that we've covered the preliminary preparations, we can focus on using Python to create our first machine learning algorithm. If you need to brush up on your Python skills, please refer to the course notes and the exercises provided. Thanks for watching! Okay, great! It is time to create our first machine learning algorithm. We will build a model and we will feed it with inputs. What we expect from the algorithm is to learn the underlying relationship of the data. Here's how we are going to approach the problem. First, we will import the relevant Python libraries for the problem at hand. Second, we will generate random data to train with. We have decided to make this example with random data, as rerunning the code will always yield different inputs. However, the model will remain the same. In this way, you can see the same methodology applied for a potentially infinite number of datasets. As this simple example is the basis for more sophisticated machine learning algorithms, it is more important to see how it works and prove that it works than acquire deep insights. We will leave the wow effect for a bit later when we deal with deep learning. Third, we will create the targets. These are the correct values. In our apartment example, they would be the actual prices properties have. Essentially, we will use fake targets to be sure there is a linear relationship. In this way, when we train the algorithm, we will be certain about the dependence it has to learn. That's a good way to prove the optimization is actually working. We know where we want to get by creating fake targets, which we would like the algorithm to figure on its own. If it does that, then we can be certain it works. Fourth, we will plot the training data so you can visually see it. This is the preparation phase of the lesson. In the second part, we will define the variables we need. We must create weights, biases, and set a learning rate. At the end, we will conclude with an actual regression. Along the way, each line of code will be explained to make sure everything is understood. Let's begin. The relevant Python libraries are NumPy and Matplotlib.pyplot. Generally, NumPy contains all the mathematical operations you will need. Moreover, it is extremely fast. For these two reasons, it is heavily used in data science. Let's import NumPy as NP, which is the conventional approach. Matplotlib is a library used for plotting data. Its module, pyplot, provides a nice interface and requires very few arguments. It is helpful when plotting data. Let's import matplotlib.pyplot as PLT. Again, that's the convention. Finally, I will also import the Axis 3D module from mpltoolkits.mplot3d, as it provides us with the ability to create 3D graphs. This is the tool we'll use to visualize the operations we're carrying out. Pyplot and Axis 3D are not essential for the machine learning algorithm. They will just provide us with good-looking plots of our data. This will provide us with an intuition of what's going on there. Anyhow, NumPy is sufficient for creating a nice algorithm on its own. Okay, this will do for now. See you in our next lesson. Let's start this lesson by generating the data we will train on. This step is not part of the machine learning algorithm. Essentially, we will create fake data with a linear relationship. Once again, we will do that to prove the methodology is working. Feel free to move on to the next lecture if you'd like. In real life, we would normally load the data from some external source, but that's a topic we'll deal with starting from our next section. Alright, if you are still here, we can generate the data. First, I will declare a variable called observations. This variable will contain the size of the dataset we want to generate. Let's work with 1,000 observations. You can do the same with 100,000 or 10 million numbers if you'd like. This choice will affect the speed of the algorithm. When we are done with this example, you can play around with the number of observations. Try 1,000, and then 100,000, and even 10 million. Be careful, as 10 million observations may cause computers to freeze. Alright, we are about to create a two-variable linear model, and the two variables will be called x and z. Let's work on the inputs. We will use the NumPy method random.uniform. It draws a random value from a specified interval, where each number has an equal chance of being selected. This method requires 3 arguments: the lowest point of the interval, the highest point of the interval, and size. The size is actually the shape in which we want to generate the data. Let's choose an interval from -10 to 10. It doesn't matter. Once again, you can play around with these numbers for homework. According to our theory, the appropriate size is the number of observations by the number of variables. So, observations by 1, as we are only talking about one variable, x. We will generate the z's in the same manner. So, These are the two input variables we will feed to the algorithm. Let's combine them in one matrix called inputs. As theory suggested, the inputs matrix will be of shape the number of observations by the number of variables, or 1000 by 2. The appropriate method to use is NP column stack. It literally stacks the observations into a matrix. This results in a matrix with dimensions 1000 by 2. Dimensionality is very important in linear algebra. We can only multiply matrices that are compatible. We want to make sure we can multiply x times w, since our linear model relies on that. In these lectures, I will print the shape of each variable, using the shape method to make sure we are working properly. The appropriate Python method is the object in question .shape. As expected, input is a matrix of size 1000 by 2, so we have worked properly. Okay. In supervised learning, we must know two major parameters, inputs and targets. We'll also have to generate targets. The weights and the biases are varied through the algorithm, and the outputs are the result from the model employed. We'll leave them to the computer. Okay, since we have only seen the linear model, we will do that in a linear model-friendly way. So, say our targets will be defined by a function f of x and z, which is equal to 2 times x minus 3 times z plus 5 plus some noise. Conceptually, the algorithm must learn this is the function. The weights are 2 and minus 3, and the bias is 5. That's the correct result. If we don't get that at the end, we haven't worked properly. You may be wondering about the noise. It is introduced to randomize our data a bit. Real data always contains noise. It's never perfect. Introducing some small noise will make the data a bit random, yet the underlying linear relationship will be retained. Let's declare the noise variable using the random.uniform method once again. I'll constrain it from -1 to +1, and its size will match the size of the x's and z's. Okay. The target values will be given according to the function we wanted. The proper line of code is targets equals 2 times the x's minus 3 times the z's plus 5 plus the noise. The targets are a linear combination of two vectors 1000 by 1, a scalar, and noise 1000 by 1. Their shape should be 1000 by 1. Let's check that. Cool. We have our inputs and the desired targets. It is time to create the algorithm. For those of you who skipped the previous lesson, I'll make a quick recap. We have our input data, which is in a 1000 by 2 matrix. In non-linear algebraic terms, this refers to a two-variable problem with 1000 observations. We also have our targets. I will quickly plot the data so we see there is a strong linear relationship. Here's the 3D plot. You don't need to do that. It's just that simple linear problems are quite visual, so we can afford to plot them. If you download the notebook file, you will see the same code with comments. Feel free to inspect it in more detail. Alright, let's re-examine the linear model. Y is equal to x times w plus b. Our algorithm will try to find such values for w and b so the outputs, y, are closest to the targets. Remember, when we performed the gradient descent, we started from an arbitrary number and then proceeded. Well, we must do the same thing now. However, this is tricky. Conventionally, we don't want to start from an arbitrary number we choose. Rather, we randomly select small initial weights. We will talk about that in more detail later. For now, let's declare a variable called init_range and set it to 0.1. That will be the radius of the range we will use to initialize the weights and the biases. Our initial weights and biases will be picked randomly from the interval -0.1 to 0.1. We will generate them as we did so far, by using the random.uniform method. The size of the weights matrix is 2 by 1, as we have two variables, so there are two weights, one for each input variable and a single output. Let's declare the bias analogically. The appropriate shape is 1 by 1. So, the bias is a scalar. In machine learning, there are many biases as there are outputs. Each bias refers to an output. If you recall the example we saw earlier about apartment prices and apartment rent, it involved two biases, as there were two outputs. I'll print the weights and the biases so you see how they look like. They are small and close to 0. These are the weights, and this is the bias. Alright. Finally, we must assign a learning rate, which we denoted with eta earlier. I'll simply select a value of 0.02. I found this learning rate useful for this demonstration. For homework, you will have to play around with it so you can see how different learning rates affect the speed of optimization. So, we are all set. We have inputs, targets, and arbitrary numbers for weights and biases. What is left is to vary the weights and biases so our outputs are closest to the targets. As we know by now, the problem boils down to minimizing the loss function with respect to the weights and the biases. And because this is a regression, we'll use 1/2 the L2 norm loss function. Okay, great. Next, let's make our model learn. Hi again. It is time to train our model. Since this is an iterative problem, we must create a loop which will apply our update rule and calculate the loss function. I'll use a for loop with 100 iterations to complete this task. Let's see the game plan we'll follow. At each iteration, we will calculate the outputs and compare them to the targets through the loss function. We will print the loss for each iteration so we know how the algorithm is doing. Finally, we will adjust the weights and biases to get a better fit of the data. At the next iteration, these updated weights and biases will provide different outputs. Then the procedure will be repeated. Alright, time to create the outputs. They are given following the well-known linear model equation. The outputs are equal to the inputs times the weights plus the biases. Multiplying matrices requires the dot method. I'll use the NumPy one. So, np dot of inputs and weights. Now, the dot product of the input times the weights is 1000 by 2. Times 2 by 1, so a 1000 by 1 matrix. When we add the bias, which is a scalar, Python adds it element-wise. This means it is added to each element of the output matrix. Okay, for simplicity, let's declare a variable called deltas, which will record the difference between the outputs and the targets. We already introduced such variable in the gradient descent lecture. Deltas equals outputs minus targets. That's useful, as it is a part of the update rule. Then we must calculate the loss. We said we will use half the L2 norm loss. Pythonically speaking, deltas is a 1000 by 1 array. We are interested in the sum of its terms, squared, following the formula for the L2 norm loss. There is a NumPy method called sum, which will allow us to sum all the values in the array. The L2 norm requires these values to be squared, so the code looks like this: np.sum of deltas squared. We then divide the whole expression by 2 to get the elegant update rules from the gradient descent. Let's further augment the loss by dividing it by the number of observations we have. This would give us the average loss per observation, or the mean loss. Similarly, to the division by 2, this does not change the logic of the loss function. It is still lower than some more accurate results that will be obtained. This little improvement makes the learning independent of the number of observations. Instead of adjusting the learning rate, we adjust the loss. That's valuable, as the same learning rate should give us similar results for both 1000 and 1 million observations. Once again, that's something we'll discuss in more detail later in the course. We'll print the loss we've obtained at each step. That's done as we want to keep an eye on whether it is decreasing as iterations are performed. If it is decreasing, our machine learning algorithm functions well. Finally, we must update the weights and biases so they are ready for the next iteration. Using the same rescaling trick, I'll also rescale the deltas. This is yet another way to make the algorithm more universal. So, The new variable is deltas underscored scaled and equals deltas divided by observations. Let's update the weights. We will follow the gradient descent logic. The new weights are equal to the old weights minus the learning rate times the dot product of the inputs and the deltas underscored scaled. The shape of the weights is 2 by 1. The shape of the inputs is 1000 by 2, and that of the deltas scaled is 1000 by 1. Obviously, we cannot simply multiply the inputs and the deltas. This is an issue that may arise occasionally due to the linear algebra involved. To fix it, we must transpose the inputs matrix using the object.t method. Now, the matrices are compatible. 2 by 1000 times 1000 by 1 is equal to 2 by 1. I'd like to spare an extra thought on that. Often, when dealing with matrices, you find the correct way to code it through dimensionality checks and compatibility errors. However, transposing matrices doesn't affect the information they hold, so we can do it freely. Alright, let's update the biases. The new biases are equal to the old biases minus the learning rate times the sum of the deltas as explained in the gradient descent lecture. This is the entire algorithm. Let's recap what it does. First, it calculates the outputs for given weights and biases. Second, it calculates a loss function that compares the outputs to the targets. Third, it prints the loss so we can later analyze it. And fourth, we update the weights and the biases following the gradient descent methodology. Let's run the code. What we get is a list of numbers that appears to be in descending order, right? These are the values of our average loss function. It started from a high value, and at each iteration, it became lower and lower, until it reached a point where it almost stopped changing. This means we have minimized or almost minimized the loss function with respect to the weights and biases. Therefore, we have found a linear function that fits the model well. The weights and the biases are optimized, but so are the outputs. Since the optimization process has ended, we can check these values. Here, we observe the values from the last iteration of the for loop, the one that gave us the lowest loss function. In the memory of the computer, the weights, biases, and outputs variables are optimized as of now. Congratulations! You learned how to create your first machine learning algorithm. Still, let's spend an extra minute on that. I'd like to print the weights and the biases. The weights seem about right. The bias is close to 5, as we wanted, but not really. That's because we used too few iterations or an inappropriate learning rate. Let's rerun the code for the loop. This will continue optimizing the algorithm for another 100 iterations. We can see the bias improves when we increase the number of iterations. We strongly encourage you to play around with the code and find the optimal number of iterations for the problem. Try different values for observations, learning rate, number of iterations, maybe even initial range for initializing the weights and biases. Cool. Finally, I'd like to show you the plot of the outputs at the last iteration against the targets. The closer this plot is to a 45-degree line, the closer the outputs are to the targets. Obviously, our model worked like a charm. Alright. This was the last lesson from our first big topic. From next on, we will start with more complicated stuff. If you have any doubts about your knowledge so far, please revisit the lessons and make use of all the extra resources available, like course notes, exercises, and Jupyter Notebooks. In addition, feel free to post in the course Q&A section. We love hearing from you. Oh, and one more thing. If you like the course so far, please leave us a review. It helps a lot. Thanks for practicing and thanks for watching. Hi again. So far, we have only used NumPy as a computational library, but as you are probably guessing, there are Python libraries tailored for machine learning. Two are TensorFlow and Scikit-learn. In this section, we will introduce TensorFlow, which will be the main tool we use throughout this course. Okay, the mathematical concept of a tensor could be broadly explained in this way. If a scalar has the lowest dimensionality and is followed by a vector and then a matrix, a tensor would be the next object in line. Scalars, vectors, and matrices are all tensors of ranks 0, 1, and 2 respectively. Tensors are simply a generalization of the concepts we have seen so far. We won't get more into the mathematics. I believe that's all you need to know. Once you see TensorFlow, you will quickly realize what I mean. Okay, before introducing TensorFlow, it'll be nice to take a minute and explain why it is a good choice. We will do so by comparing it to Scikit-learn, as they are two of the most popular libraries, and most other machine learning courses are based on Scikit-learn. Right. You probably know it, but Google is a leader in machine learning. It is also one of the great innovators in the field because of the Google Brain team. As machine learning was developing, Google needed better programming methods to suit their needs. That is why they developed the TensorFlow package for internal use. At the end of 2015, Google released TensorFlow to the public. Now, it is probably the leading library for neural networks, including deep neural networks, convolution neural networks, and recurrent neural networks. One of the biggest advantages of TensorFlow is it uses not only the CPU of the computer, but also its GPU. This is crucial for the speed of the algorithm, as, in this way, TensorFlow utilizes much more computing power. Recently, Google furthered this trend by introducing TPUs, or Tensor Processing Units, which improves performance even further. TensorFlow is one of the cutting-edge technologies available right now and is likely here to stay. We said an alternative of TensorFlow is Scikit-learn. If you have done any machine learning but haven't used TensorFlow, you are probably familiar with the Scikit-learn or Scikit-learn library. It is very powerful and widely adopted. However, Scikit-learn does not offer the same functionality as TensorFlow regarding neural networks. Having said that, we can make the opposite point for other fields of machine learning. In the presence of problems such as k-means clustering and random forests, Scikit-learn or Matplotlib could be a better fit, even though TensorFlow started to make way. That is especially true when it comes to pre-processing, as we will see later. This course focuses on neural networks. We aim to provide you a deep understanding of neural networks. Instead of scratching the surface, we decided to go deeper by introducing TensorFlow. In the lessons you will see next, we will do just that. We will start by introducing TensorFlow's underlying logic. Then we will create the same minimal example, but this time using the new logic. We will continue introducing machine learning theory and its implementation through TensorFlow. It is very important to know the machine learning theory is the same for both TensorFlow, Scikit-learn, or whatever package you are using. The only difference is the underlying code you'll write. That's our outline. Stay tuned. Okay, this is our actual TensorFlow intro. Once again, TensorFlow is a machine learning library developed by Google. It allows us to construct fairly complicated models with little coding. To give you perspective, our practical example required 20 lines of code. With TensorFlow, it will still be 20 lines of code. No difference whatsoever. However, the last exercise we will see in this course would require a few hundred lines of code using NumPy. With TensorFlow, around 50. Moreover, 20 of those would be almost the same as the ones in our minimal example. TensorFlow is an amazing framework, and you will see that by the end of the course. However, it has a peculiar underlying logic. Remember when you first studied linear algebra or trigonometry? The logic differed greatly from the mathematics you had seen before, right? Well, it's the same with TensorFlow. Once you start working with it, it's super easy, but you must make an extra effort to understand it properly. Let's do that. The most basic notion we'll need to define is the computational graph. Quoting TensorFlow's About section at tensorflow.org, nodes in the graph represent mathematical operations, while the edges represent the multi-dimensional data arrays, or tensors, communicated between them. We won't be drawing computational graphs, but that's how such a graph looks. Simple as that. Okay, let's start coding, and we'll grasp the rest of our intuition on the go. Naturally, we'll start by importing the TensorFlow library. We will import TensorFlow as TF. Then, we will generate fake data once again. This code is virtually the same as the one we used before. There is a single line of code difference. Let's look at it. For each project you work on, you'll have a dataset. Perhaps you are used to XLSX or CSV files. However, TensorFlow doesn't work well with them. It is tensor-based, so it likes tensors. Therefore, we want a format that can store the information in tensors. One solution to this problem is NPZ files. That's basically NumPy's file type. It allows you to save ND arrays or n-dimensional arrays. Thinking like computer scientists, we can say tensors can be represented as multi-dimensional arrays. When we read an NPZ file, the data is already organized in the desired way. Often, this is an important part of machine learning preprocessing. You are given data in a specific file format. Then you open it, preprocess it, and finally save it into an NPZ. Later, you build your algorithm using the NPZ instead of the original file. So, back to the code. As you can see, we have called the inputs and targets we generated inputs and generated targets. Next, we can simply save them into a tensor-friendly file. The proper way to do that is to use the npsaves method. It involves several arguments. The first one is the file name. It is written in quotation marks. I'll call it tf_intro. Then we must indicate the objects we want to save into the file. The syntax is as follows. The label we want to assign to the ND array equals the array we want to save under that label. For us, the label is inputs and is equal to the generated inputs array. Similarly, the targets are equal to the generated targets. Note, it is not required to call them inputs and targets. If we would like to, we could call them with arbitrary names, such as rad1 and rad2. Executing the code would save the tf_intro file in the same directory as the Jupyter Notebook we are using. Okay, in our next lecture, we will define our model. Thanks for watching. Okay, great. We will create two variables that measure the size of our inputs and outputs. The input size is 2, as there are two input variables, the x's and the z's we saw earlier, and the output size is 1, as there is only one output y. Okay, these two lines of code assign the values 2 and 1 to the variables input size and output size. That's programming you are familiar with, nothing new so far. Time for the peculiar TensorFlow logic. Each object we will create using the TensorFlow library would do nothing unless explicitly told to. It would rather describe the logic of the machine learning algorithm, but won't assign values or execute anything. Remember that, as it is crucial. Time to define our first TensorFlow object, the placeholder. Let's see the line of code that allows us to do that. Inputs equals tf.placeholder of tf.float32, comma, square brackets, none, input size. The placeholder is where we feed the data. The data contained in our dataset would go into a placeholder. Naturally, we feed both inputs and targets. Let's include the code for the targets. The data in the NPZ file contained exactly the inputs and the targets. We will use the NPZ to feed data into the model through the placeholders. The float32 indicates the type of data we want. 32 bits float precision is sufficient for most calculations. Finally, we have the dimensions of the two placeholders. The input's dimensions are none by input size. The input size is the number of input variables we have. The none you see here doesn't mean the data has no dimension. Instead, it means we need not specify it. That's useful for us, lazy users. We need not know the number of observations or keep track of it. TensorFlow does that for us. We are only interested in the number of input variables. As you can see, this isn't much different from our linear model. The dimensions we are working with are n by k, where n is the number of observations and k is the number of variables. Okay. Similarly, the size of the targets is none by the output size. That's natural, since outputs and targets have the same shape. Remember, nothing has happened yet. We have instructed the algorithm how we will feed data, but no data has been fed. Alright. The next thing we would like to do is define the weights and biases. They are declared using the other basic TensorFlow object, variable. Variables preserve their value across iterations, while placeholders don't. Allow me to elaborate, please. Let's say we have two inputs, A and B, and two targets, C and D. A goes into the input's placeholder. Through the weights and biases, we can obtain an output. Then, we compare the output with the target C. Depending on the comparison, we'll vary the weights and biases and continue with the next iteration. Then B goes into the input's placeholder. Through the updated weights and biases, we calculate the new output, which will then be compared to the second target, D. Then, we'll adjust the weights and biases once again. Okay, A and B came and went away. We fed them to the model, got the best out of them, and we no longer need them. The weights and biases, however, were preserved throughout the iterations we performed. More precisely, we updated them and kept their updated version using the information provided by A and B. This is the same process we carried out before, but we used a different wording to describe it. We feed the data in the placeholders and vary the variables. Simple as that. Let's define the variables. The proper method is tf.variable. The expression you see within the brackets show us how the variables will be initialized. We will use the random uniform method to be consistent with the minimal example shown earlier. This is something we'll discuss in more detail later in the course. Notice we have the same shapes as the one we had in our framework. We've prepared the inputs, weights, biases, and targets. We still need the outputs. The outputs of our model are the product of the linear combination of the inputs times the weights plus the biases. The proper syntax in TensorFlow is outputs equals tf.matmul of inputs and weights plus the biases. Matmul relates to the same concept as the dot product, but generalized for tensors. In the brackets, we plug in what we want to multiply. So, this is our linear model, right? Before we can continue, I would like to ask you a question. What will happen if I run the code? Nothing! Our model will do nothing. It doesn't initialize the weights or biases, nor it plugs in any values. It certainly doesn't calculate any outputs. It lays the logic through which this will happen later. That's what TensorFlow logic is all about. Okay, now that we have placeholders, variables, and mathematical operations all set up, we can pause here. In our next lesson, we will choose a loss function and an optimization method for our model. Thanks for watching. Okay, let's see where we are in terms of our machine learning framework. We have the data and the model. What we need is an objective function and an optimization algorithm. The loss function we used in the practical example was the average L2 norm loss divided by 2. Let's call it mean loss. In TensorFlow, its syntax would be mean loss equals tf.losses.mean squared error of the targets and outputs divided by 2. Let's consider this in more detail. TF is our library. There is a module called losses. Losses contains most of the common loss functions. Then, from losses, we call the method mean_squared_ error, which is the average L2 norm loss. Mean_squared_ error has two arguments. labels, and predictions. The labels are the targets, as we discussed earlier. In supervised learning, we must assign labels, which are the correct values. Obviously, the labels are the targets. The second argument of the mean_squared_ error is the predictions following our model. These are the outputs. Finally, we'll divide by 2, so the code is the same as in the previous example. Working with TensorFlow, this is an adjustment we no longer need. I will only keep it for consistency. The not after the number 2 is added there, so we will be certain we'll obtain a float. This is a good programming habit that will save you lots of trouble. Okay, so what does this line of code do? It only defines the objective function we will use. That's it. It is time to introduce the optimization method. Let's call it optimize. Optimize equals tf.train.gradient descent optimizer of learning underscore rate equals 0.05 dot minimize of mean underscore loss. The method train contains the most common optimization algorithms. The gradient descent optimizer is the one we will use. Naturally, there are other optimization algorithms besides this one. We will talk about some of them in the next sections of the course. The learning rate is an argument of the optimizer, and this is where we set it. Finally, we must minimize the loss function that we called mean loss. Okay, we used 7 lines of code to define all the relationships in our model, the loss function, and the optimization algorithm. In the TensorFlow world, not a single operation has been executed just yet. We've built all the passages and roller coasters our data will go through, but we have not opened the gates for any of it yet. There is a special syntax when we want to do that. The proper method is tf.interactiveSession braces. I will declare a variable, ses, equal to this operation. In this way, I will only need to write ses, not the whole interactive session method when I want to execute something. The name ses is short for session. That's the conventional way to declare a session. In TensorFlow, the training happens in these so-called sessions. When we use the interactive session method, we actually say, it's time to execute. Alright, in our next lecture, we will finally make the algorithm learn. Thanks for watching. The entire framework is ready. It is time for the algorithm to learn. We said that's done by varying the weights and the biases. Before this happens though, we must set the arbitrary values from which weights and biases start. This is the process known as initialization. So, let the initializer be equal to tf.globalVariablesInitializer brackets. That's the method that initializes all tensor objects marked as variables. We have 2, weights and biases. They will be the only ones affected. Okay, did we initialize? No, we haven't executed yet. So how do we execute? Execution is done through the method run applied to the session. For each execution, we must type ses.run, and in brackets will indicate what we want to run. Therefore, to initialize the variables, we must write ses.run initializer. Awesome! The variables have been initialized. Around this time, we usually import the data. Our training data comes from the NPZ we saved a couple lessons ago. So, training data equals npload, tfintro.npz. Once again, this method will only load the file if it is in the same directory on your computer. Otherwise, we must specify the entire path. What is left is the for loop that would minimize the loss function. So, for e in range 100, semicolons. E stands for epoch. Each iteration over the full dataset in machine learning is called an epoch. From now on, we'll use this term to describe iterations and number of iterations. We still have 2 lines of code we must go through. Hold on tight, please. Let's call the loss at the current epoch cur loss. This is basically the same as we had earlier. We will calculate the loss function at the end of each iteration or epoch. Let's look at the syntax in TensorFlow. Cur loss is equal to sys.run, of course, since we want to execute something. Then, in parentheses, we have two arguments. The first argument is a list in which we must state what we want to run. In this case, we would like to run the optimization declared earlier. I will also compute the mean loss, as I want to be able to print it later. The second argument is feed_dict. It tells the algorithm how the data is going to be fed. The syntax is feed_dict equals braces. Now we must instruct it which placeholder is fed what. First, we put the placeholder, so inputs semicolons. Then, we feed it from the training data, the tensor called inputs. That's the syntax. Recall that training data was where we located the NPZ file. The two labels of the NPZ file were inputs and targets and are self-explanatory. Similarly, the targets come from our NPZ and were labeled targets. So, we have comma, targets, semicolons, training data, targets. And finally, we must close all the brackets we used. That's it. The meaning of this line of code is the following. Run the optimize and mean loss operations by filling the placeholder objects with data specified in the feed_dict parameter. Cool. There is a little programming trick some of you may not have seen. Since every method returns something, the cur_loss will actually return something for optimize and something for the mean loss. The mean loss is a value, and we already saw that. However, optimize doesn't return anything. Its output is always none. The underscore is a special symbol to disregard a return value of a function. We don't need the return value of optimize, so we'll disregard it. Okay. Finally, I'll print the loss at each epoch. That's our final machine learning algorithm created with TensorFlow. There are just 10 lines of code specific to the problem. Let's run it. Naturally, we get the same result. We can further plot the data. I won't go through the code, but you can see the explanation related to it in the course resources. The point is that the graph is the same as before. Alright, there is no need to comment on the actual result. It is far more interesting to comment on the use of TensorFlow. Notice that the loop we used was so generic we can apply this exact same code for different machine learning algorithms. It calculates the current loss, given an optimizer, a loss function, inputs, and targets. All these arguments were defined before the loop using the TensorFlow structure. Whenever we need to build a new model, we can change the appropriate objects rather than modify the loop or structure as a whole. TensorFlow code is extremely reusable. Further on, we will see that iterating through the data is not always so simple if we want amazing results. This proves useful in real life, as the code you'll need doesn't need to be adjusted too much, and it is easy to share your code with others. Okay, this was our introduction to TensorFlow. In the next few lessons, we will dig deeper into the theory of neural networks. Please complete the exercises, as they will introduce you to additional TensorFlow concepts. Good luck, and thanks for watching. Hi again. It's time to dig deeper. The pun is intentional, as we will explore deep neural networks. Now, in one of the earlier sections, we saw how to train a simple linear regression model. It had two inputs and a single output. That's a type of neural network, but it had no depth. We used a linear model that learned a function. This function was the best fit of the data according to the L2 norm loss, with a couple of hundred iterations. Now, most real-life dependencies cannot be modeled with a simple linear combination, and because we want to be better forecasters, we'll need better models. Most of the time, this means working with a model that is more sophisticated than a linear model. Such complexity is usually achieved by using both linear and nonlinear operations. Mixing linear combinations and nonlinearities allow us to model arbitrary functions, or in other words, functions with strange, unconventional shapes. Like this one. So basically, our model changes from inputs that are linearly combined, resulting in outputs, to inputs that are linearly combined, and then go through some nonlinear transformation resulting in outputs. Probably, you will be happy to see an example of nonlinearity. Well, here's one. A commonly used nonlinearity is the sigmoid function, defined as sigma x equals 1, divided by 1 plus e to the power of minus x. Intriguing. The initial linear combination and the added nonlinearity form a layer. The layer is the building block of neural networks. When we have more than one layer, we are talking about a deep neural network. Henceforth, layers will be an important topic. Thanks for watching. We said we will talk extensively about layers. Time to keep our promise. Here's arguably the most common pictorial representation of deep neural networks. This is our first layer. It is called the input layer. That's basically the data we have. We take the inputs and get outputs, as we did before. The main rationale behind neural networks, however, is that we can now use these outputs as inputs for another layer, and then another one, and another, until we decide to stop. The last layer we build is the output layer. That's basically what we compare the targets to. Alright, so the first layer is the input layer, and the last layer is the output layer. All the layers between are called hidden layers. We call them hidden as we know the inputs and we get the outputs, but we don't know what happens between, as these operations are hidden. Stacking layers one after the other produces a deep network, or, as we will call it, a deep net. The building blocks of the hidden layer are called hidden units or nodes. Here's a hidden unit. In mathematical terms, if H is the tensor related to the hidden layer, each hidden unit is an element of that tensor. The number of hidden units in a hidden layer is often referred to as the width of the layer. Usually, but not always, we stack layers with the same width so that the layer width is equal to the width of the entire network. Okay, we saw how wide a deep network is. Let's examine how deep it can be. Depth is an important ingredient, as it refers to the number of hidden layers in a network. When we create a machine learning algorithm, we choose its width and depth. We refer to these values as hyperparameters. Hyperparameters should not be mistaken with parameters. Recall that parameters were the weights and the biases. Hyperparameters are the width, depth, learning rate, and some other variables we will see later. The main difference between the two is that the value of the parameters will be derived through optimization, while hyperparameters are set by us before we start optimizing. Alright, this will do for now. Thanks for watching. We already saw this picture, right? However, I sense we didn't spend enough time on it. It is a fundamental illustration of deep nets. Whatever we do, we will come back to it, as it is simple yet so insightful. In this lesson, we'll spend extra time examining it thoroughly. The first layer you see is the input layer. Each circle represents a separate input. So, in this graph, we have 8 inputs. These inputs are the data we feed to train the model. In the TensorFlow framework, this is the placeholder for inputs. Remember the weather forecast example? Well, imagine it has 8 inputs. For instance, average temperature, highest temperature, lowest temperature, humidity, precipitation, atmospheric pressure, cloud cover, and visibility in the distance. Now remember, we combine these inputs linearly and then add nonlinearity. How can we do that? Well, linearity is easy. We'll just use the good old linear model. Its inputs are the x, and to combine them linearly, we need weights. In this example, the weights are an 8 by 9 matrix. 1 by 8 times 8 by 9 will give us an object with a shape of 1 by 9. Therefore, following this operation, we will get a vector of length 9, or a 1 by 9 matrix. This is exactly the number of hidden units we have in the first hidden layer. Okay, all these arrows will get us from the inputs to the first hidden layer. Each arrow represents the mathematical transformation of a certain value. So, a certain weight is applied, then a nonlinearity is added. Note that the nonlinearity doesn't change the shape of the expression. It only changes its linearity. Okay, So arrows represent weights and nonlinearities, right? But how many weights are there? The weights matrix was 8 by 9, so there are 72 weights. Well, guess what? We also have 72 arrows. 9 arrows go out of each input unit and into a hidden unit. Since we have 8 input units, this gives us 72 arrows. To be even more specific, each weight has 2 index numbers. The first one indicates the input it is referring to, while the second one indicates the hidden unit it is referring to. For example, weight 36 is applied to the third input and is involved in calculating the sixth hidden unit. In the same way, weights 16, 26, and so on until 86 all participate in computing the sixth hidden unit. They are linearly combined, and then nonlinearity is added in order to produce the sixth hidden unit. In the same way, we get each of the other hidden units. Alright, then what? Well, then we have the first hidden layer. Using the same logic, we can linearly combine the hidden units and apply a nonlinearity, right? Indeed. This time though, there are 9 input hidden units and 9 output hidden units. Therefore, the weights will be contained in a 9 by 9 matrix, and there will be 81 arrows. Finally, we apply nonlinearity, and we reach the second hidden layer. We can go on and on and on like this. We can add 100 hidden layers if we want. That's a question of how deep we want our deep net to be. And, of course, we will talk about that later in the course. Finally, we'll have the last hidden layer. When we apply the operation once again, we will reach the output layer. The output units depend on the number of outputs we would like to have. In this picture, there are 4. They may be the temperature, humidity, precipitation, and pressure for the next day. To reach this point, we will have a 9 by 4 weights matrix, which refers to 36 arrows or 36 weights, exactly what we expected. Alright, as before, our optimization goal is finding values for weight matrices that would allow us to convert inputs into correct outputs as best as we can. This time though, we are not using a single linear model, but a complex infrastructure with a much higher probability of delivering a meaningful result. Okay, I'm sure you know how powerful machine learning can be, right? At least that's how I felt when I was introduced to this picture. We are doing great, and we shouldn't stop here. There's plenty of work and learning ahead of us. After explaining the logic behind deep nets, there is a tiny detail we still must discuss. I bet you are wondering why we need those nonlinearities after each linear combination to create the next layer. Well, in the next lesson, we'll tackle this issue. We said nonlinearities are needed so we can represent more complicated relationships. While that is true, it isn't the full picture. An important consequence of including nonlinearities is the ability to stack layers. Stacking layers is the process of placing one layer after the other in a meaningful way. Remember that. It's fundamental. The point we will make is that we cannot stack layers when we have only linear relationships. Let's prove it. Imagine we have a single hidden layer and there are no nonlinearities. So, our picture looks this way. There are 8 input nodes, 9 hidden nodes in the hidden layer, and 4 output nodes. Therefore, we have an 8 by 9 weights matrix for the linear relationship between the input layer and the hidden layer. Let's call this matrix W1 and the hidden units H. According to the linear model, H is equal to X times W1. Let's ignore the biases for a while. So, our hidden units are summarized in the matrix H with a shape of 1 by 9. Now, let's get to the output layer from the hidden layer. Once again, according to the linear model, Y is equal to H times W2. We have W2 as these weights are different. We already know the H matrix is equal to X times W1, right? Let's replace H in this equation. Y is equal to X times W1 times W2. But W1 and W2 can be multiplied, right? What we get is a combined matrix, W star, with dimensions 8 by 4. Well then, our deep net can be simplified into a linear model, which looks this way. y equals x times w star. Knowing that, we realize the hidden layer is completely useless in this case. We can just train this simple linear model and we would get the same result. In mathematics, this seems like an obvious fact, but in machine learning, it is not so clear from the beginning. The two consecutive linear transformations are equivalent to a single one. Even if we add 100 layers, the problem would be simplified to a single transformation. That is the reason we need nonlinearities. Without them, stacking layers one after the other is meaningless. And without stacking layers, we will have no depth. What's more, with no depth, each and every problem will equal the simple linear example we did earlier. And many practitioners would tell you it was borderline machine learning. Alright, let's summarize in one sentence. To have deep nets and find complex relationships through arbitrary functions, we need nonlinearities. Point taken. Thanks for watching. Welcome back. We've talked about nonlinearities for some time now, without elaborating in more detail, and that's a topic we would like to address in this lesson. In a machine learning context, nonlinearities are also called activation functions. Henceforth, that's how we will refer to them. Activation functions transform inputs into outputs of a different kind. Think about the temperature outside. Assume you wake up and the sun is shining, so you put on some light clothes. You go out and feel warm and comfortable. You carry your jacket in your hands. In the afternoon, the temperature starts decreasing. Initially, you don't feel a difference. At some point though, your brain says, it's getting cold. You listen to your brain and put on your jacket. The input you got was the change in the temperature. The activation function transformed this input into an action. Put on the jacket or continue carrying it. This is also the output after the transformation. It is a binary variable, jacket or no jacket. That's the basic logic behind nonlinearities. The change in the temperature was following a linear model as it was steadily decreasing. The activation function transformed this relationship into an output linked to the temperature but was of a different kind. Okay, in machine learning, we have different activation functions, but there are a few used much more frequently than others. Here is a table with 4 of the most commonly used activation functions. Let's go through one row to see how the table is organized. First, we have the sigmoid, also known as the logistic function. Here is its formula. Next to it, we have its derivative. As you may recall, the derivative is an essential part of the gradient descent. Naturally, when we work with TensorFlow, we won't need to calculate the derivative, as TensorFlow does that automatically. Anyhow, the purpose of this lesson is understanding these functions, their graphs and ranges, in a way that would allow us to acquire intuition about the way they behave. Here's the function's graph. And finally, we have its range. Once we have applied the sigmoid as an activator, all the outputs will be contained in the range from 0 to 1. So, the output is somewhat standardized. Alright, here are the other 3 common activators. The tanh, also known as the hyperbolic tangent, the ReLU, aka the rectified linear unit, and the softmax activator. You can see their formulas, derivatives, graphs, and ranges. The softmax graph is not missing. The reason we don't have it here is that it is different every time. Pause this video for a while and examine the table in more detail. You can also find this table in the course notes. So, all these functions are activators, right? What makes them similar? Well, let's look at their graphs. All are monotonic, continuous, and differentiable. These are important properties needed for the optimization process. As we are not there yet, we will leave this issue for later. Before we conclude, I would like to make this remark. Activation functions are also called transfer functions because of their transformation properties. The two terms are used interchangeably in machine learning context, but have differences in other fields. Therefore, to avoid confusion, we will stick to the term activation functions. Alright, let's wrap it up here. Thanks for watching. Let's continue exploring this table, which contains mostly Greek letters. We said the softmax function has no definite graph. Why so? Well, this function is different. If we take a careful look at its formula, we would see the key difference between this function and the other is it takes an argument the whole vector a instead of individual elements. So, the softmax function is equal to the exponential of the element at position I, divided by the sum of the exponentials of all elements of the vector. So, while the other activation functions get an input value and transform it, regardless of the other elements, the softmax considers the information about the whole set of numbers we have. Time for an example. Let a be equal to xw plus b, which is our well-known model. Then, we can say the output of y will be the softmax of a. Let's look at a hidden layer with 3 units. So, a here is equal to hw plus b. After transforming it through a linear combination, we obtain a vector a with 3 elements, minus 0.21, 0.47, and 1.72. Now, if we used a different activation, such as the sigmoid, we would simply apply the formula for each of the 3 numbers, and we would obtain a new vector containing 3 new numbers. But softmax is special. Each element in the output depends on the entire set of elements of the input. Let's find the softmax of a. First, I'll calculate the denominator. It is given by e to the power of minus 0.21 plus e to the power of 0.47 plus e to the power of 1.72. That's approximately 8. Then, we must divide each exponential by this denominator to get the new vector. The result is 0.1, 0.2, and 0.7. This is our output layer. Okay. A key aspect of the softmax transformation is that the values it outputs are in the range from 0 to 1. Their sum is exactly 1. What else has such a property? Probabilities? Yes, probabilities. Indeed, the point of the softmax transformation is to transform a bunch of arbitrarily large or small numbers that come out of previous layers and fit them into a valid probability distribution. This is extremely important and useful. Remember our example with cats, dogs, and horses we saw earlier? One photo was described by a vector containing 0.1, 0.2, and 0.7. We promised we will tell you how to do that. Well, that's how. Through a softmax transformation. We kept our promise. Now that we know we are talking about probabilities, we can comfortably say we are 70% certain the image is a picture of a horse. This makes everything so intuitive and useful that the softmax activation is often used as the activation of the final output layer in classification problems. So no matter what happens before, the final output of the algorithm is a probability distribution. Alright, this will do for now. Thanks for watching. Backpropagation. The most intuitive lesson, yet the hardest to grasp in mathematical terms. We will first explore the intuition behind it, then look into the mathematics. Okay? And yes, math is optional, but we would like to encourage you to look at it to gain a better understanding. You shouldn't skip this lesson though, as it's the fun part of backpropagation. First, I'd like to recap what we know so far. We've seen and understood the logic of how layers are stacked. We've also explored a few activation functions and spent extra time showing they are central to the concept of stacking layers. Moreover, by now, we have said 100 times that the training process consists of updating parameters through the gradient descent for optimizing the objective function. In supervised learning, the process of optimization consisted of minimizing the loss. Our updates were directly related to the partial derivatives of the loss and indirectly related to the errors, or deltas as we called them. Let me remind you that the deltas were the differences between the targets and the outputs. Alright, as we will see later, deltas for the hidden layers are trickier to define. Still, they have a similar meaning. The procedure for calculating them is called backpropagation of errors. Having these deltas allows us to vary parameters using the familiar update rule. Let's start from the other side of the coin, forward propagation. Forward propagation is the process of pushing inputs through the net. At the end of each epoch, the obtained outputs are compared to the targets to form the errors. Then, we backpropagate through partial derivatives and change each parameter so errors at the next epoch are minimized. For the minimal example, the backpropagation consisted of a single step, aligning the weights given the errors we obtained. Here's where it gets a little tricky. When we have a deep net, we must update all the weights related to the input layer and the hidden layers. For example, in this famous picture, we have 270 weights. And yes, this means we had to manually draw all 270 arrows you see here. So, updating all 270 weights is a big deal. But wait, we also introduced activation functions. This means we have to update the weights accordingly, considering the used nonlinearities and their derivatives. Finally, to update the weights, we must compare the outputs to the targets. This is done for each layer, but we have no targets for the hidden units. We don't know the errors. So how do we update the weights? That's what backpropagation is all about. We must derive the appropriate updates as if we had targets. Now, the way academics solve this issue is through errors. The main point is that we can trace the contribution of each unit, hidden or not, to the error of the output. Okay, in the next lesson, we will provide an illustration of the backpropagation concept. Thanks for watching. Okay, great. Let's look at the schematic illustration of backpropagation shown here. Our net is quite simple. It has a single hidden layer. Each node is labeled, so we have inputs x1 and x2. Hidden layer units, output layer units y1 and y2. And finally, the targets t1 and t2. The weights are w11, w12, w13, w21, w22, and w23 for the first part of the net. For the second part, we named them u11, u12, u21, u22, u31, and u32, so we can differentiate between the two types of weights. That's very important. We know the error associated with y1 and y2, as it depends on known targets. So let's call the two errors E1 and E2. Based on them, we can adjust the weights labeled with U. Each U contributes to a single error. For example, U11 contributes to E1. Then, we find its derivative and update the coefficient. Nothing new here. Now, let's examine W11. W11 helped us predict H1. But then, we needed H1 to calculate Y1 and Y2. Thus, it played a role in determining both errors, E1 and E2. So, while U11 contributes to a single error, W11 contributes to both errors. Therefore, its adjustment rule must be different. The solution to this problem is to take the errors and backpropagate them through the net, using the weights. Knowing the U weights, we can measure the contribution of each hidden unit to the respective errors. Then, once we've found out the contribution of each hidden unit to the respective errors, we can update the W weights. So essentially, through backpropagation, the algorithm identifies which weights lead to which errors. Then, it adjusts the weights that have a bigger contribution to the errors by more than the weights with a smaller contribution. A big problem arises when we must also consider the activation functions. They introduce additional complexity to this process. Linear contributions are easy, but nonlinear ones are tougher. Imagine backpropagating in our introductory net. Once you understand it, it seems very simple. While pictorially straightforward, mathematically, it is rough to say the least. That is why backpropagation is one of the biggest challenges for the speed of an algorithm. In the next two lessons, we'll explain the mathematics behind backpropagation. If you would like to acquire a deep understanding of deep nets, we encourage you to proceed and watch them. Otherwise, feel free to skip to the next topic we'll examine: overfitting. One of the most commonly asked questions at data science interviews is about overfitting. A recruiter will probably bring up the topic and will ask you, what's overfitting and how do we deal with it? Fortunately, in this lesson, we'll address this issue and you won't be surprised when it comes up. There are two concepts that are interrelated: underfitting and overfitting. They go together. Understanding one helps us understand the other and vice versa. Okay. Broadly speaking, overfitting means our training has focused on the particular training set so much it has missed the point. Underfitting, on the other hand, means the model has not captured the underlying logic of the data. It doesn't know what to do and therefore provides an answer that is far from correct. Let's explain this with graphs, as it is much more intuitive and cooler. First, we will look at a regression, and then we'll consider a classification problem. Here, we can see several data points following the blue function with some minor noise. A good algorithm would result in a model that looks like this. It is not perfect, but it is very close to the actual relationship. Okay. We can certainly say a linear model would be an underfitting model. It provides an answer, but does not capture the underlying logic of the data. It doesn't have strong predictive power. It's kind of lame. Underfitted models are clumsy. They have high costs in terms of high loss functions, and their accuracy is low. You quickly realize that either there are no relationships to be found, or you need a more complex model. Alright, let's check an overfitted model. Here it is. Now that you see this picture, we can say overfitting refers to models that are so super good at modeling the training data that they fit or come very near each observation. The problem is that the random noise is captured inside an overfitted model. Let me elaborate on this a little further with an example. Imagine you are trying to predict the euro-dollar exchange rate based on 50 common indicators. You train your model and get low costs and high accuracies. In fact, you believe, with 99.99% accuracy, you can predict the exchange rate. Confident with your machine learning skills, you start trading with real money. Unfortunately, most orders you place fail miserably. In the end, you lose all your money because you trusted the amazing model so much. What happened with your model is it probably overfit the data. It was trained to explain the training data so well that it missed the point. Instead of finding the dependency between the euro and the dollar, you modeled the noise. The noise in this case consists of the random decisions of the investors participating in the market at that time. So, shouldn't the computer be smarter than that, you may ask? Well, we explained the training data well, so our outputs were close to the targets. The loss function was low, and the learning process worked like a charm in mathematical terms. However, once we go out of the training set and meet the real-life situation, we see our model is actually quite bad. First rule of programming states that the computer is never wrong. It is us who made a mistake. We must keep issues as overfitting in mind and take care of them with the appropriate remedies. As a whole, overfitting can be quite tricky. After seeing this beautiful graph, you probably believe you can spot an overfitting problem. But remember that, in the Forex example, there were 50 indicators, which means we need a 51-dimensional graph, and I don't know about you, but my senses work in 3 dimensions only. Don't worry, we will explore how to deal with overfitting in the next few lessons. But first, we will look at a classification example. Stay tuned. Time for our classification example. The 2 main types of supervised learning are regression and classification, and we are trying to show you the most concepts in terms of both regression and classification. We'll do the same here. Here's our example. There are 2 categories. One of them is cats, and the other one is dogs. A good model explaining all the data looks like this: a quadratic function with a few errors. Following the logic we saw in our previous example, what would be an underfitted model? Well, of course, a linear model. Linear models are not very smart. Often, a simple linear model underfits if the data is not transformed. Around 60% of the observations would be classified correctly with an underfitted model. Now, an overfitted model would classify the observations perfectly, right? It has correctly identified all the cat and dog photos in the dataset. But, once we give it a different dataset, following the same quadratic function logic, it will perform poorly. Alright, let's conclude lesson with the following remark. What is a well-trained model then? Well, it is somewhere between an underfitting and an overfitting model. This fine balance is often called the bias-variance trade-off. Oh, and if you are a meme fan, there's this Facebook page, Machine Learning Memes for Convolutional Teens, that I follow. Some time ago, they posted a photo of a bed that beautifully exemplifies overfitting. It fits some people perfectly, but on average, miss the point of being a bed. Memes are an interesting way to check knowledge. If you find it funny, you most probably understand the concept. As you can see, we are back to our interesting conceptual lessons, so stick around and thanks for watching. I believe the previous lessons convinced you that overfitting is the real enemy when it comes to machine learning. We also said we will teach you how to deal with it. That's precisely what we'll do in this lesson. To prevent overfitting, one must be able to identify it first. Let's start with that. Usually, we'll be able to spot overfitting by dividing our available dataset into 3 subsets: training, validation, and test. The first one is the training dataset. As its name suggests, it helps us train the model to its final form. As you should know, that's the place where we perform everything we've seen until now. Nothing is new here, since so far, we thought all data is training data. But we intentionally labeled the Python variables training data instead of data in the exercises. Okay, let's check out the other 2 subsets. The validation dataset is the one that will help us detect and prevent overfitting. Let's see how that works. All the training is done on the training set. In other words, we update the weights for the training set only. Every once in a while, we stop training for a bit. At this point, the model is somewhat trained. What we do next is take the model and apply it to the validation dataset. This time, we just run it without updating the weights, so we only propagate forward, not backward. In other words, we just calculate its loss function. On average, the loss function calculated for the validation set should be the same as the one of the training set. This is logical, as the training and validation sets were extracted from the same initial dataset containing the same perceived dependencies. Normally, we would perform this operation many times in the process of creating a good machine learning algorithm. The 2 loss functions we calculate are referred to as training loss and validation loss. And because the data in the training set is trained using the gradient descent, each subsequent loss will be lower or equal to the previous one. That's how gradient descent works by definition. So, we are sure the training loss is being minimized. That's where the validation loss comes in play. At some point, the validation loss could start increasing. That's a red flag. We are overfitting. We are getting better at predicting the training set, but we are moving away from the overall logic data. At this point, we should stop training the model. Let's illustrate this with the same example we used in the last lesson. We start from an underfitting position. By increasing the complexity of the model, we reach a very good model. The training cost is going down, the validation cost is moving accordingly. At some point though, we start overfitting. As you can see, the training loss is still decreasing, while the validation loss is increasing. That's when we should stop. Alright, it is extremely important that the model is not trained on validation samples. This will eliminate the whole purpose of the above-mentioned process. The training set and the validation set should be separate without overlapping each other. Cool. See you in our next lesson, and thanks for watching. In the previous lesson, we introduced the validation dataset. In addition, we said we want to divide the initial dataset into 3 parts: training, validation, and the topic of this lesson. After we have trained the model and validated it, it is time to measure its predictive power. Logically, this is done by running the model on a new dataset it hasn't seen before. That's equivalent to applying the model in real life. So, our dataset is trained and validated. We have the final version of the machine learning black box, right? We are ready to test it with the test dataset. The accuracy of the prediction we get from this test is the accuracy we would expect the model to have if we deploy it in real life. So, the test dataset is the last step we take. Let's summarize. First, you get a dataset. Then, you split it into 3 parts. Here's where you would probably like to ask a question. Do we split the dataset evenly? How do practitioners approach this? Well, there is no set rule, but splits like 80% training, 10% validation, and 10% test, or 70-20-10, are commonly used. Obviously, the dataset where we train the model should be considerably larger than the other two. You want to devote as much data as possible to the training of the model while having enough samples to validate and test on. Third, we train the model using the training dataset and the training dataset only. Fourth, every now and then, we validate the model by running it for the validation dataset. That's where you would probably like to ask a second question. What does every now and then mean? Glad you asked. Usually, we validate the dataset for every epoch. Every time we adjust all weights and calculate the training loss, we validate. If the training loss and the validation loss go hand in hand, we carry on training the model. If the validation loss is increasing, we are overfitting, so we should stop. Fifth and final step. You test the model with the test dataset. The accuracy you obtain at this stage is the accuracy of your machine learning algorithm. Alright, these topics are getting more interesting, aren't they? Keep up the good work, and I'll see you in our next video. In the last few lessons, we explained why we should split the dataset into three parts: training, validation, and test. This is a standard mechanism, and usually, when machine learning is appropriate, we have enough data to apply it. What if we have a small dataset? We can't afford to split it into three datasets, as we will lose some of the underlying relationships. Or worse, we can have so little data left for training that the algorithm cannot learn anything. There is another answer to this issue, and it's called n-fold cross-validation. This is a strategy that resembles the general one, but combines the train and validation datasets in a clever way. However, it still requires a test subset. We are combining the training and validation steps, but we can't avoid the test stage. Alright, let's say we have a dataset containing 11,000 observations. We'll save 1,000 observations for the test. What we are left with are 10,000 samples. Please notice this dataset is not very big. In data science, we often deal with ginormous datasets. Or at least that's the hope. Side note, ginormous datasets have their own big problem. Being so large, they often have a lot of missing values. Such a dataset is usually referred to as being sparse. This introduces a whole new spectrum of issues. In any case, we want to train on 9,000 data points and validate on 1,000. We'll split the remaining data into 10 subsets containing 1,000 observations each. We fold it 10 times. So, this is a 10-fold cross-validation. 10 is also a commonly used value, and that's why we picked it for this illustration. We treat one subset as a validation set, while the other 9 combined as a training set. Visually, it looks this way. We have 10 combinations. The orange set is the validation one, while the blue ones are the training sets. During the first epoch, the first chunk of data serves as validation. Then in the second epoch, the second chunk of data serves as validation, and so on. In this way, for each epoch, we don't overlap training and validation, as it should be. Moreover, we manage to use the whole dataset, except for the test part. As with all good things, this comes at a price. We have still trained on the validation set, which was not a good idea. It is less likely that the overfitting flag is raised, and it is possible that we overfitted a bit. The trade-off is between not having a model or having a model that's a bit overfitted. N-fold cross-validation solves the scarce data issue, but should by no means be used as the norm. Whenever you can, divide your dataset into three parts: training, validation, and test. Only if it doesn't manage to learn much because of data scarcity, you should try the n-fold cross-validation. Okay, this will do for now. Thanks for watching. There is one last detail related to overfitting we should examine more carefully. We said a dozen times we trained the model until the loss function is minimized. We can go on doing that forever, but at some point we'll overfit. That is why we introduced the validation dataset and said a thing or two about breaking the training process. In this lesson, we will explore additional rules that will indicate our model has been trained. The proper term is early stopping. Generally, early stopping is a technique to prevent overfitting. It is called early stopping as we want to stop early, before we overfit, that is. Let's explore the most common ways to do that. The simplest one is to train for a preset number of epochs. In the minimal example after the first section, we trained for 100 epochs. This gave us no guarantee that the minimum has been reached or passed. A high enough learning rate would even cause the loss to diverge to infinity. That's something you should have tried for homework. Still, the problem was so simple that, rookie mistakes aside, very few epochs would cause a satisfactory result. However, our machine learning skills have improved so much, and we shouldn't even consider using this naive method. A bit more sophisticated technique is to stop when the loss function updates become sufficiently small. We even had a note on that when we introduced the gradient descent. A common rule of thumb is to stop when the relative decrease in the loss function becomes less than 0.001 or 0.1%. This simple rule has two underlying ideas. First, we are sure we won't stop before we have reached a minimum. That's because of the way gradient descent works. It will descend until a minimum is reached. The loss function will stop changing, making the update rule yielding in the same weights. In this way, we'll be stuck in the minimum. The second idea is that we want to save computing power by using as few iterations as possible. As we said, once we have reached the minimum or diverged to infinity, we will be stuck there. Knowing that a gazillion more epochs won't change a thing, we can just stop there. This saves us the trouble of iterating uselessly without updating anything. That's obviously a level up from the previous method. While the preset number of epochs approach may ultimately minimize the loss, chances are we can't guess the number of required epochs. Probably the algorithms would have performed thousands of iterations that did not update the weights. Obviously, each epoch that changes nothing is useless and should be dropped. Alright, so the first technique didn't deal with any problems except for minimizing the loss. The second technique optimized the cost and saved computing power, but both can lead to tremendous overfitting. It's only natural that we need a more advanced technique. Yes, we are talking about the validation set strategy. This is the simplest clever technique for early stopping that prevents overfitting. Let me state the rule once again, using the proper figure. A typical training occurs this way. As time goes by, the error becomes smaller. The distribution is exponential, as initially we are finding better weights quickly. The more we train the model, the harder it gets to achieve an improvement. At some point, it becomes almost flat. Now, if we put the validation curve on the same graph, it would start with the training cost. At the point when we start overfitting, the validation cost will start increasing. Here's the point at which the two functions begin diverging. That's our red flag. We should stop the algorithm before we do more damage to the model. Okay, now, depending on the case, different types of early stopping can be used. The preset number of iterations method was used in the minimal example. That wasn't by chance. The problem was linear and super simple. A more complicated method for early stopping would be a stretch. The second method that monitors the relative change is simple and clever, but doesn't address overfitting. The validation set strategy is simple and cleverer, and it prevents overfitting. However, it may take our algorithm a really long time to overfit. It is possible that the weights are barely moving and we still haven't started overfitting. That's why I like to use a combination of both methods. So, my rule would be: stop when the validation loss starts increasing or when the training loss becomes very small. That's about it. Thanks for watching. Hey, this is our first lesson about initialization, which is a crucial part of machine learning. When you use clumsy or inappropriate methods, even the fastest computer in the world won't be able to help you. As they say, the devil's in the detail, and this saying is as true as it gets for initialization. Okay. Initialization is the process in which we set the initial values of weights. It was important to add to this section to the course, as an inappropriate initialization would cause an unoptimizable model. Let's revise what we have seen so far. When we introduce the simplest gradient descent, we use the function 5 times x squared plus 3 times x minus 4. We performed the gradient descent in Excel, and you should have that file available. If you remember, we arbitrarily chose 4 as an initial value. In other words, we initialized a weight with a value of 4. The next occasion on which we stumbled upon initial weights was our simple example. Back then, we initialized them randomly in the range -0.1 to 0.1. If you haven't asked yourself this question, now is the time. Does it really matter what the initial weights are? Well, we wouldn't create a whole section about it if it didn't. In the minimal example, we said we will need random initial weights, but we didn't elaborate why. Okay, you can see the same scheme we used here for our backpropagation lessons. This is a model with a single hidden layer. Let's initialize our weights and biases in such a way that they are equal to a constant. It doesn't matter which constant. As you can see, the 3 hidden units are completely symmetrical with respect to the inputs. Each hidden unit is a function of one weight coming from x1 and one from x2. If all the weights are equal, there is no reason for the algorithm to learn that h1, h2, and h3 are different. Forward propagating, there is no reason for the algorithm to think that even our outputs are different. Based on this symmetry, backpropagating, all the weights are bound to be updated without distinguishing between the different nodes in the net. Some optimization would still take place, so it won't be the initial value. Still, the weights would remain useless. Alright, nice to know that. So, how are we supposed to initialize the weights then? We'll see this in our next lesson. Stay tuned. Now that we know initialization matters, let's see how we can deal with it. A simple approach would be to initialize weights randomly within a small range. We did that in the minimal example. We used the NumPy method, random uniform, and our range was between -0.1 and 0.1. This approach chooses the values randomly but in a uniform manner. Each one has the exact same probability of being chosen. Equal probability of being selected sounds intuitive, but it is important to stress it. You will soon see why. Really soon. Here's a second approach. We could choose a normal initializer. The idea is basically the same. This time though, we pick the numbers from a zero mean normal distribution. The chosen variance is arbitrary, but should be small. As you can guess, since it follows the normal distribution, values closer to 0 are much more likely to be chosen than other values. An example of such initialization is to draw from a normal distribution with a mean 0 and a standard deviation 0.1. Both methods are somewhat problematic, although they were the norm until 2010. It was just recently that academics came up with a solution. Let's explore the problem. Weights are used in linear combinations. Then the linear combinations are activated. Once more, we will use the sigmoid activator. The sigmoid, as other commonly used nonlinearities, is peculiar around its mean and its extremes. Activation functions take as inputs the linear combination of the units from the previous layer, right? Well, if the weights are too small, this will cause values that fall around this range. In this range, unfortunately, the sigmoid is almost linear. If all our inputs are in this range, which will happen if we use small weights, the sigmoid would not apply a nonlinearity, but a linearity to the linear combination. As we discussed, nonlinearities are essential for deep nets. Conversely, if the values are too large or too small, the sigmoid is almost flat, which causes the output of the sigmoid to be only ones or only zeros, respectively. A static output of the activations minimizes the gradient, while the algorithm is not really trained. So, what we want is a wide range of inputs for the sigmoid. These inputs depend on the weights, so the weights will have to be initialized in a reasonable range, so we have a nice variance along the linear combinations. In the next lesson, we will explore how to do that. Thanks for watching. Okay, in this lesson, we'll continue talking about initializations. A more advanced strategy is the Xavier initialization, also known as Glorot initialization. Who are Xavier and Glorot, you could ask? Well, that's one person actually, Xavier Glorot. He is the only academic I know of whose work is named after his first name, rather than his last name. Quite intriguing. In any case, Mr. Glorot, or simply Xavier, proposed this method in 2010 and was quickly adopted on a large scale. That's the state-of-the-art technique, so you probably want to get acquainted with it. So, the range for the first two cases was arbitrarily chosen by us, right? The Xavier initialization addresses this issue. There are both a uniform Xavier initialization and a normal Xavier initialization. The main idea is that the method used for randomization isn't so important. It is the number of outputs in the following layer that does. With the passing of each layer, the Xavier initialization is maintaining the variance in some bounds, so we can take full advantage of activation functions. There are two formulas. The uniform Xavier initialization states we should draw each weight W from a random uniform distribution in the range from minus x to x, where x is equal to the square root of 6, divided by the number of inputs plus the number of outputs for the transformation. For the normal Xavier initialization, we have draw each weight W from a normal distribution with a mean of 0 and a standard deviation equal to 2, divided by the number of inputs plus the number of outputs for the transformation. The numerator values 2 and 6 vary across sources, but the idea is the same. Another detail you should notice is that the number of inputs and outputs matters. Outputs are clear. That's where the activation function is going. So the higher number of outputs, the higher need to spread weights. What about inputs? Well, optimization is done through backpropagation, so when we backpropagate, we would obviously have the same problem but in the opposite direction. Okay, finally, in TensorFlow, this is the default initializer. So, if you initialize the variables without specifying how, it will automatically adopt the Xavier initializer, unlike what we did in the minimal example. Super interesting stuff. Next time, we will challenge the gradient descent. Thanks for watching. Hi, and welcome back. This is our section about optimization, which in this context refers to the algorithms we will use to vary our model's parameters. So far, we've seen the gradient descent only, and now it is time to discuss improvements that will lead to enhanced algorithms. Most of what we have learned is invaluable from a theoretical viewpoint, but slow when it comes to practical execution. However, there are simple steps to take to turn things around. Let's start with the clumsiest optimizer, the gradient descent. The GD, short for gradient descent, iterates over the whole training set before updating the weights. Each update is very small. That's due to the whole concept of the gradient descent, driven by the small value of the learning rate. As you remember, we couldn't choose a value too high, as this jeopardizes the algorithm. Therefore, we have many epochs, over many points, using a very small learning rate. This is slow. It's not descending, it's basically snailing down the gradient. Fortunately for us, there is a simple solution to the problem. It's a similar algorithm called the SGD, or the stochastic gradient descent. It works in the exact same way, but instead of updating the weights once per epoch, it updates them in real time inside a single epoch. Let's elaborate on that. The stochastic gradient descent is closely related to the concept of batching. Batching is the process of splitting data into n batches, often called mini batches. We update the weights after every batch, instead of every epoch. Let's say we have 10,000 training points. If we choose a batch size of 1,000, then we have 10 batches per epoch. So, for every full iteration over the training data set, we would update the weights 10 times, instead of 1. This is by no means a new method. It is the same as the gradient descent, but much faster. As all good things go, the SGD comes at a cost. It approximates things a bit. So, we lose a bit of accuracy, but the trade-off is worth it. That's confirmed by the fact that virtually everyone in the industry uses stochastic gradient descent, not gradient descent. So, why does this speed up the algorithm so drastically? Was it worth talking about it for 3 minutes? There are a couple of reasons, but one of the finest is related to hardware. Splitting the training set into batches allows the CPU cores or the GPU cores to train on different batches in parallel. This gives an incredible speed boost, which is why practitioners rely on it. Okay, one last thing. Actually, stochastic gradient descent is when you update after every input, so your batch size is 1. What we have been talking about was technically called mini-batch gradient descent. However, more often than not, practitioners refer to the mini-batch GD as stochastic gradient descent. If you are wondering, the plain gradient descent we talked about at the beginning of the course is called batch GD, as it has a single batch. Okay, perfect. Now we can confidently close this topic. Thanks for watching. Hey, I've been waiting for this lecture for almost the entire course. It is of utmost importance, but it would not have made sense to show it earlier. So far, we have seen both the gradient descent and the stochastic gradient descent. They are the logical ways to train our models. Let's say this is the graph of our loss function. A gradient descent algorithm would begin here and start descending. A single batch GD would be slow, but eventually reach the minimum in a consistent manner. A stochastic gradient descent algorithm would move through a greater number of points, but much faster. At the end, it is likely we'll get an approximate answer, rather than the exact one. Still, as we said in the previous lecture, with the saving in terms of computation speed, it is well worth the trade-off. In real life though, loss functions are not so regular. What if I told you this was not the whole graph of the loss function? It was just one of its minima, a local imposter rather than the sought extremum. Zooming out, we see that, actually, the global minimum of the loss is this point. Each local minimum is a suboptimal solution to the machine learning optimization. Gradient descent is prone to this issue. Often, it falls into the closest minimum to the starting point, rather than the global minimum. Of course, it depends on the learning rate as well. A higher learning rate may miss the first local minimum and fall directly into the global valley. However, it is likely to oscillate and never reach it. We'll talk more about the learning rate in our next lessons. For now, let's focus on the gradient descent. So, does this mean the gradient descent optimization method is not almighty? Not necessarily. Remedies can be applied to reach the desired result. Well, if this lesson was about realizing this problem exists, the next one will address the solution. Stay tuned and thanks for watching. As we promised, in this lecture, we will explore additional ways to improve our chances of reaching the global minimum, rather than getting stuck in a local one. The gradient descent and the stochastic gradient descent are good ways to train our models. We need not change them, we should simply extend them. The simplest extension we should apply is called momentum. What is momentum? An easy way to explain momentum is through a physics analogy. Imagine the gradient descent as rolling a ball down a hill. The faster the ball rolls, the higher is its momentum. A small dip in the grass would not stop the ball. It would rather continue rolling until it has reached a flat surface, out of which it cannot go. The small dip is the local minimum, while the big valley is the global minimum. If there wasn't any momentum, the ball would never reach the desired final destination. It would have rolled with some non-increasing speed and would have stopped in the dip. The momentum accounts for the fact that the ball is actually going downhill. Now, in our gradient descent framework so far, we didn't consider momentum. There is no reason to ignore it. Therefore, we created algorithms that will likely fall into a dip, if there was one, instead of descending to the optimal solution. So, how do we add momentum to the algorithm? The rule so far was Wi equals W minus eta times the gradient of the loss with respect to W. Including momentum, we will consider the speed with which we've been descending so far. For instance, if the ball is rolling fast, the momentum is high. Otherwise, the momentum is low. The best way to find out how fast the ball rolls is to check how fast it rolled a moment ago. That's also the method adopted in machine learning. We add the previous update step to the formula. We want to multiply it by some coefficient, otherwise we would assign the same importance to the current update and the previous one. Usually, we use an alpha of 0.9 to adjust the previous update. Alpha is a hyperparameter, and we can play around with it for better results. 0.9 is the conventional rule of thumb, and this is what I also use. Alright, we considered momentum. In the next lesson, we will look at the learning rate, one of the key hyperparameters of the algorithm. Thanks for watching. Hi again. We introduced the concept of hyperparameters 20 or 30 lessons ago. I'm sure you remember parameters are the weights and the biases. Hyperparameters are things like width and depth of the algorithm, the number of hidden units and the number of hidden layers. It is up to us to choose their values. We mentioned we should play around with hyperparameters to find the best suit for our algorithm and data at hand. This lesson will focus on another hyperparameter, the learning rate eta. What do we know so far? It must be small enough, so we gently descend through the loss function, instead of oscillating wildly around the minimum and never reaching it, or diverging to infinity. It also had to be big enough so the optimization takes place in a reasonable amount of time. In the Excel file we provided on the gradient descent for one parameter, you could play around with the learning rate. Moreover, in one exercise coming with the minimal example, you had the same chance, but for the linear model. Okay, we are doing science here, so these phases, small enough and big enough, are too vague. A smart way to deal with choosing the proper learning rate is adopting a so-called learning rate schedule. Learning rate schedules get the best of both worlds, small enough and big enough. The rationale is the following. We start from a high initial learning rate. This leads to faster training. In this way, we approach the minimum faster. Then we want to lower the rate gradually as training goes. Around the end of the training, we want a very small learning rate, so we get an accurate solution. How are learning schedules implemented in practice? There are two basic ways to do that. The simplest one is setting a predetermined piecewise constant learning rate. For example, we can use a learning rate of 0.1 for the first 5 epochs, then 0.01 for the next 5, and 0.001 until the end. This causes the loss function to converge much faster to the sought minimum and will give us an accurate result. However, considering what we've learned so far, this seems too simple to be the norm, right? Indeed, it is crude, as it requires us to know approximately how many epochs it will take the loss to converge. Still, beginners may want to use it, as it makes a great difference compared to the constant learning rate. Okay. A second, much smarter approach is the exponential schedule. The exponential schedule is a much better alternative, as it smoothly reduces or decays the learning rate. We usually start from a high value, such as eta naught equal to 0.1. Then we update the learning rate at each epoch using the rule. In this expression, n is the current epoch, while c is a constant. Here's the sequence of learning rates that would follow for a c equal to 20. There is no rule for the constant c, but usually it should be the same order of magnitude as the number of epochs needed to minimize the loss. For example, if we need 100 epochs, values of c from 50 to 500 are all fine. If we need 1000, values from 500 to 5000 are alright. Usually, we'll need much less, so a value of c around 20 or 30 works well. However, from my personal experience, the exact value of c doesn't matter as much. What makes a big difference is the presence of the learning schedule itself. C is also a hyperparameter. As with all hyperparameters, it may make a difference for your particular problem. You can try different values of c and see if this affects the results you obtain. It's worth pointing out that all those cool new improvements, such as learning rate schedules and momentum, come at a price. We pay the price of increasing the number of hyperparameters for which we must pick values. Generally, the rule of thumb values work well, but bear in mind that, for some specific problem of yours, they may not. It's always worth it to explore several hyperparameter values before sticking with one. Okay, this will do for now. Thanks for watching. Time for a short lesson. Just talking about the learning rate without seeing it doesn't inform us as well as seeing a graph. As they say, a picture is worth 1,000 words. we can see a graph of the loss as a function of the number of epochs. So far, we have only seen this case. We used a small learning rate, which reached the goal, but slowly. As we said, a high learning rate would minimize the loss fast, but only to a certain extent. Then it starts oscillating, and the loss stops moving. A high learning rate would not even minimize the loss. The cost would rather explode upwards as seen in the graph. Finally, a well-selected learning rate, such as the one defined by the exponential schedule, would minimize the loss much faster than a low learning rate. Moreover, it would do so more accurately than a high learning rate. Naturally, we are aiming at the good learning rate. Problem is, we don't know what this learning rate is for our particular data and model. One way to establish a good learning rate is to plot the graph we're showing you now for a few learning rate values, and pick the one that looks the most like the good curve. Note that high learning rates may not minimize the loss. A low learning rate eventually converges with the good learning rate, but the process will take much longer. Alright, I'm sure this was useful and cleared doubts you had. Take care, and thanks for watching. As with other things in deep learning, we can dig deeper into the learning rate schedules. Instead of using a simple rule to adjust the learning rate, we can use advanced academic research on this topic. We will consider two types of adaptive learning rates, ADA-grad and RMS-prop. They build on each other, so it won't be too much to take in. Be prepared to see many formulas, although it's unnecessary to learn these by heart. In TensorFlow, you can simply say, use ADA-grad and the magic will happen. As usual, we recommend you go through the entire video, as what we will see is cutting-edge machine learning. When you practice machine learning, you must be able to choose the best methods for training your models. Alright, let's begin. First, we have the ADA-grad. ADA-grad is short for Adaptive Gradient Algorithm. It was proposed in 2011, so it is new. It dynamically varies the learning rate at each update and for every weight individually. So, the original rule was, stated otherwise, the change in W equals minus the learning rate times the partial derivative of the loss with respect to W. Nothing new so far. When we consider the adaptive gradient algorithm, the change in the weight will be given by the same expression, but in addition, it will be divided by the square root of g at time t plus epsilon. So what is g here? G is the adaptation magic. Gi at epoch t equals Gi at epoch t minus 1 plus the square of the gradient at epoch t. We begin at g not equal to 0. At each step, g increases because we are adding two non-negative numbers. Thus, g is a monotonously increasing function. Since we are dividing the learning rate, eta, by a monotonously increasing function, eta divided by that is obviously monotonously decreasing. If you are wondering, the epsilon is some small number we need to put there, because if g is 0, we won't be able to perform the division. Okay, that was ADA-grad. It is basically a smart adaptive learning rate scheduler. Adaptive stands for the fact that the effective learning rate is based on the training itself. It is not a preset learning schedule like the exponential one where all the eta values are calculated regardless of the training process. Another very important point is that the adaptation is per weight. This means every individual weight in the whole network keeps track of its own g function to normalize its own steps. It's an important observation, as different weights do not reach their optimal value simultaneously. The second method is RMS-prop, or the root mean square propagation. It is very similar to ADA-grad. The update rule is defined in the same way, but the g function is a bit different. The two terms are assigned weights, beta and 1 minus beta respectively, effectively keeping track of a moving average of the g values. This new hyperparameter beta is a number between 0 and 1. The value 0.9 is very typical. We had a similar situation with the alpha in the momentum section. The great implication here is that the function is no longer monotonously increasing. Hence, eta divided by the square root of g is not monotonously decreasing. Empirical evidence shows that, in this way, the rate adapts much more efficiently. Okay, both methods are very logical and smart. However, there is a third method based on these two, which is superior. We will explore it in our next lecture. Thanks for watching. So far, we saw two different optimizers. Each brought a new bright idea to the update rule. It would be even better if we can combine these concepts and obtain even better results, right? Okay, let's see how this is done. If we take the learning rate schedules and the momentum, we can reach a state-of-the-art optimization algorithm that I find most useful. It's called the adaptive moment estimation. It is the most advanced optimizer applied in practice. It's also new, as it was proposed on the 22nd of December 2014. Stated differently, if somebody you know studied machine learning in university in 2014 or 2015, he probably did not see this method. This also reinforces the idea that your ML preparation doesn't stop after a course you take. The trends are ever changing, and you should stay informed and up to date. Back to ADAM. ADAM is the topic of this lesson and is short for Adaptive Moment Estimation. If you noticed, the ADA grad and the RMS prop did not include momentum. ADAM steps on RMS prop and introduces momentum into the equation. So, the update rule, derived from RMS prop, changes from delta Wi equals minus eta divided by g at epoch t plus epsilon times the gradient to delta Wi equals minus eta divided by g at epoch t plus epsilon times mi at epoch t. M is the momentum we discussed earlier, but it is a bit transformed. M at epoch t equals alpha times m at epoch t minus 1 plus 1 minus alpha times the gradient. Naturally, m naught is equal to 0. I always use ADAM as it is a cutting-edge machine learning method. Take a moment to appreciate what you've seen in the previous few lectures. Starting from the basic gradient descent procedure, we first extended it to the SGD for computational efficiency. Then, we introduced an adaptive learning rate scheduler to reach ADA grad. We further extended it by introducing a moving average for the scheduler in RMS prop. Finally, we introduced momentum in the final expression for ADAM. Of course, as with all science, data science is a long chain of academic research building on top of each other. Alright, see you in our next lesson. Thanks for watching. Hey, this is the last theoretical section of the course. It is about the first activity you want to do when you start creating a machine learning algorithm. Pre-processing. Pre-processing refers to any manipulation we apply to the dataset before running it through the model. Everything we saw so far was conditioned on the fact that we had already pre-processed our data in a way suitable for training. You've already seen some pre-processing. In the TensorFlow intro, we created an NPZ file. All the training we did came from there. So, if you must work with data in an Excel file, CSV, or whatever, saving it into an NPZ file would be a type of pre-processing. In this section, though, we will mainly focus on data transformations, rather than reordering as before. What is the motivation for pre-processing? There are several important points. The first one is about compatibility with the libraries we use. As we saw earlier, TensorFlow works with tensors and not Excel spreadsheets. In data science, you will often be given data in whatever format, and you must make it compatible with the tools you use. Second, we may need to adjust inputs of different magnitude. Let's say we are Forex traders. If one input we are working with is the end of the day euro-dollar exchange rate, it would be a value around 1. However, if another input is the daily trading volume, we would have values like 100,000 and higher. Obviously, the orders of magnitude are quite different. A linear combination of numbers based on such different scales is problematic. In purely mathematical terms, A value of 1 is negligible regarding a value of 100,000. As all the inputs are on an equal footing in a vector or a matrix, the algorithm is likely to ignore all values around 1. These values essentially represent the euro-dollar exchange rate itself, so they are often more important than the volume of trading. Obviously, something needs to be done to solve this issue. A third reason is generalization. Problems that seem different can often be solved by similar models. Standardizing inputs of different problems allows us to reuse the exact same models. Sometimes, there are cases when we can even reuse already trained networks. Imagine that! You have trained a model previously. You face a new problem, you test your model, and it works like a charm. That's not unusual in machine learning. In the next few lessons, we will focus on these concepts and introduce several pre-processing techniques. Thanks for watching! We will start with one of the simplest transformations. Often, we are not interested in an absolute value, but a relative value. That's usually the case when working with stock prices. If you open Google and type Apple stock price, what you'll get is Apple stock price, but with red or green numbers, the relative change in Apple stock price. This is an example of pre-processing that is so common we don't consider it as such. Relative metrics are especially useful when we have a time series data, like stock prices, forex exchange rates, and so on. Still in the world of finance, we can further transform these relative changes into logarithms. Many statistical and mathematical methods take advantage of logarithms as they facilitate faster computation. In machine learning, log transformations are not as common, but can increase the speed of learning. Okay, great. So this is one type of pre-processing we wanted to give as an example. Let's continue to our next lesson, where we will deal with pre-processing transformations that are more typical for the world of machine learning. Stick around, and thanks for watching. The most common problem when working with numerical data is about the difference in magnitudes as we mentioned in the first lesson. An easy fix for this issue is standardization. Other names by which you may have heard this term are feature scaling and normalization. However, normalization could refer to a few additional concepts even within machine learning, which is why we will stick with the term standardization and feature scaling. Standardization or feature scaling is the process of transforming the data we are working with into a standard scale. A very common way to approach this problem is by subtracting the mean and dividing by the standard deviation. In this way, regardless of the dataset, we will always obtain a distribution with a mean of 0 and a standard deviation of 1, which could easily be proven. Let's show that with an FX example. Say our algorithm has two input variables, euro-dollar exchange rate and the daily trading volume. We have 3 days worth of observations. First day 1.3 and 110,000. Second day 1.34 and 98,700. And the third day 1.25 and 135,000. The first value shows the euro-dollar exchange rate, while the second one shows the daily trading volume. Let's standardize these figures. We standardize the euro-dollar exchange rates regarding the other euro-dollar exchange rates. So, we look at 1.3, 1.34, and 1.25. The mean is 1.3, while the standard deviation 0.045. Going through the above-mentioned transformation, these values become 0.07, 0.96, and minus 1.03 respectively. Standardizing trading volumes, we obtain minus 0.25, minus 0.85, and 1.1. In this way, we have focused figures of very different scales to appear similar. That's why another name for standardization is feature scaling. This will ensure our linear combinations treat the two variables equally. Also, it is much easier to make sense of the data. The transformation of trading volumes allowed us to transform the volumes from 110,000, 98,700, and 135,000 to minus 0.25, minus 0.85, and 1.1. In this way, The third term is considerably higher than the average, while the first one is around the average. We can confidently say that 135,000 traits per day is a high figure, while 98,700 is low. Please disregard the simplification of having just 3 observations. That's just an example. Besides standardization, there are other popular methods too. We will shortly introduce them without going too much in detail. Initially, we said that normalization refers to several concepts. One of them, which comes up in machine learning, often consists of converting each sample into a unit-length vector using the L1 or L2 norm. Another pre-processing method is PCA, standing for Principal Components Analysis. It is a dimension reduction technique, often used when working with several variables referring to the same bigger concept, or latent variable. For instance, if we have data about one's religion, voting history, participation in different associations, and upbringing, we can combine these 4 to reflect his or her attitude towards immigration. This new variable will normally be standardized in a range with a mean of 0 and a standard deviation of 1. Whitening is another technique frequently used for pre-processing. It is often performed after PCA and removes most of the underlying correlations between data points. Whitening can be useful when conceptually the data should be uncorrelated, but that's not reflected in the observations. We can't cover all the strategies, as each strategy is problem-specific. However, standardization is the most common one, and is the one we will employ in the practical examples we will face in this course. In the next lesson, we will see how to deal with categorical data. Thanks for watching! So far, most of what we've seen were examples of numerical variables, exchange rates, trading volume, security prices, and so on. Often, though, we must deal with categorical data. In short, categorical data refers to groups or categories, such as our cat-dog examples. But the machine learning algorithm takes only numbers as values, doesn't it? Therefore, the question when working with categorical data is, how to convert a cat category into a number so we can input it into a model or output it in the end. Obviously, a different number should be associated with each category, right? Or better, a tensor. We are getting closer. Imagine our shop has 3 products: bread, yogurt, and muffins. Now, how do we convert these categories to numbers? A possible solution could be to enumerate them like this: bread equals 1, yogurt equals 2, muffins equals 3. Unfortunately, this implies there is some order. It's like saying that a muffin is more than a yogurt, which is more than bread. Think about prices. If we instead had 3 prices, $1, $2, and $3, 3 times $1 is equal to $3. Using the same logic, does it make any sense to you that 3 times bread equals 1 muffin? There is another level of ambiguity. To get from bread to muffins, we always go through yogurt. Ultimately, what we have done is assume the data has some order while it hasn't. Typically, that's an issue when our data is divided into categories. Think about the products in a shop, about different car brands, or about people. So, our question becomes, how to encode such categories in a way which will be useful for a machine learning algorithm? 2 main ways are adopted. The first one is called one-hot encoding, and the other binary encoding. We will see how to perform them in the next lesson. Thanks for watching! Hi, and welcome back. Let's begin this lesson by introducing binary encoding. We will start from the ordinal numbers we assigned earlier. Bread is represented by the number 1, yogurt by the number 2, and muffin is designated with 3. Binary encoding implies we should turn these numbers into binary. 1 in binary is 0, 1, so bread would be 0, 1. 2 in binary is 1, 0, so yogurt would be 1, 0. 3 in binary is 1, 1, so muffins would be 1, 1. The next step of the process is to divide these into different columns as if we were creating 2 new variables. For the first one, bread is 0, yogurt is 1, and muffins are 1. For the second variable, bread is 1, yogurt is 0, and muffins are 1. We have differentiated between the three categories and have removed the order. However, there are still some implied correlations between them. For instance, bread and yogurt seem exactly the opposite of each other. It's like we are saying, whatever is bread is not yogurt, and vice versa. Even if this makes sense, if we encode them in a different way, this opposite correlation would be true for muffins and yogurt, but no longer for bread. Therefore, binary encoding proves problematic, but is a great improvement regarding the initial ordinal method. Alright, finally, we have the so-called one-hot encoding. One-hot is very simple and widely adopted. It consists of creating as many columns as there are possible values. Here, we have 3 products. Thus, we need 3 columns or 3 variables. Let's call them bread, yogurt, and muffins. Imagine these variables as asking the question, is this product bread? Is this product yogurt? And is this product muffins? 1 means yes, 0 means no. So, for a product that is bread, we will have 1, 0, 0. For a product that is yogurt, 0, 1, 0. And for a product that is muffin, 0, 0, 1. This is very intuitive, as a product can only be of one type at the same time. Thus, there will be only one value 1, and everything else will be zeroed. This means the products are uncorrelated and unequivocal, which is useful and usually works like a charm. Many lessons ago we were talking about cats, dogs, and horses classification. The target vectors there were one-hot encoded, so we had the same type of vectors. There is one big problem with one-hot encoding though. One-hot encoding requires a lot of new variables. For example, IKEA offers around 12,000 products. Do we want to include 12,000 columns in our inputs? Definitely not. If we used binary, the 12,000 products would be represented by 16 columns only, since the 12,000th product would be written like this in binary. This is exponentially lower than the 12,000 columns we would need for one-hot encoding. In such cases, we must use binary, even though that would introduce some unjustified correlations between the products. Clearly, there is a trade-off between binary and one-hot encoding. We would prefer one-hot when we have a few categories, and binary when dealing with many categories. Alright, that was all. Thanks for watching. I know it has been a long way before we start coding, but all the lessons so far were necessary to understand what we are doing. Your patience will now pay off when we start coding. It would have been easy to introduce TensorFlow, provide you a template, and tell you put this here, put that there. However, now that you know the theory, you can truly understand the whole process and everything going on. Alright, the problem we have chosen is the hello world of machine learning, as often as this is one of the first problems students encounter. It is called MNIST classification. The MNIST dataset consists of around 70,000 images of handwritten digits. Since we have 10 digits, there are 10 classes, from 0 to 9. Our subject is to build an algorithm that takes as input an image and then correctly determines which number is shown in that image. There are a few reasons we started with this algorithm. Initially, we wanted to create an example not used before. But then we thought there is a reason MNIST is the hello world of machine learning. First, it's a visual problem. You can see the data and you know what to expect. This makes the problem easy to define and understand. Second, it has been tested by almost everyone who ever touched a machine learning algorithm. We want our students to know what people are talking about when they say, you know, when I first did the MNIST, I thought this and that. Third, it is easy for you to build up your convolutional neural networks from the MNIST example. And finally, the dataset is very big. It is well divided into training and test, and there aren't any missing values or wrong labels. It is a perfect dataset. Of course, we should credit the creators. The dataset was developed by Yann LeCun, Corina Cortez, and Christopher Burgess. You can find more about it on Yann LeCun's website at yann.lecun.com. Yann is one of the founding fathers of convolutional neural networks and modern image recognition. He is the director of AI research at Facebook. As you can imagine, doing machine learning at Facebook involves a lot of work with images, so Yan is not only a pioneer, but a leader in AI research and implementation. Okay, in the next lesson, we will outline the solution to the MNIST problem. Thanks for watching. How are we going to approach this image recognition problem? Each image in the MNIST dataset is 28 pixels by 28 pixels. It's on a grayscale, so we can think about the problem as a 28 by 28 matrix, where input values are from 0 to 1. For example, a handwritten 7 in a matrix would look like this. That's an approximation, but the idea is more or less the same. Now, because all images are of the same size, a 28 by 28 photo will have 784 pixels. The approach for deep networks is to transform or flatten each image into a vector of length 784. So, for each image, we would have 784 inputs. Each input corresponds to the intensity of the color of the corresponding pixel. We will have 784 input units in our input layer. Then we will linearly combine them and add a nonlinearity to get the first hidden layer. For our example, we will build a model with 2 hidden layers. 2 hidden layers are enough to produce a model with very good accuracy. Finally, we will produce the output layer. There are 10 digits, so 10 classes. Therefore, we will have 10 output units in the output layer. The output will then be compared to the targets. We will use one-hot encoding for both the outputs and the targets. For example, the digit 0 will be represented by this vector, while the digit 5 by that one. Okay, since we would like to see the probability of a digit being rightfully labeled, we will use a softmax activation function for the output layer. It is easy to talk about these problems now that you've been through the course, isn't it? So, let me walk you through the action plan. You will quickly notice our curriculum so far has covered everything you need. First, we must outline the model and choose the activation functions we want to employ. Second, we must use the proper TensorFlow syntax to describe our placeholders, variables, and the related operations. Third, we must choose the appropriate advanced optimizers. Fourth, we will divide the dataset into batches for faster learning. Fifth, we will initialize the variables and we will be ready to learn. Sixth, we will make it learn. The algorithm will backpropagate its way to accuracy. At each epoch, we will validate. We will also place some early stopping. Finally, we will test the accuracy of the model regarding the test dataset. Alright, let's get to it. Alright, let's start by importing the packages we'll need for this exercise. As usual, we'll import NumPy as NP and TensorFlow as TF. TensorFlow includes a data provider for MNIST we will use. To get it, we must import input data from TensorFlow Examples Tutorials MNIST. This function automatically downloads the MNIST dataset to the directory of the Jupyter Notebook you are working on. The dataset has been split into training, validation, and test. Furthermore, the data has been pre-processed in a simple and useful format. All these points are useful for us, as we can simply focus on building the machine learning algorithm. Finally, we must read the data with this line of code. MNIST equals input data dot read datasets of MNIST data and one-hot equals true. That's the recommended way to approach the MNIST problem, according to TensorFlow's website. You can read the full documentation by clicking on the link we've provided. The data is hosted on Yan LeCun's website, while the built-in functions related to this example can be found on tensorflow.org. We will use all built-in capabilities for this example, and then create our own when we tackle the big practical example later in the course. Alright, let's run the code. It takes some time to do that, as we are actually downloading the whole dataset. Don't worry, this is done only once. In the next lesson, we will outline our model. Thanks for watching. Alright, great! It is time to outline our model. Consider pausing the video here if you feel like you need to revisit the introduction of TensorFlow we showed a few lessons ago. In this way, it'll be easier for you to see the parallels between the two exercises, and you'll know what to expect. Moreover, I'll go through the familiar parts of the code faster without wasting time on things we already know. Okay, I'll start outlining the model. Let's start by drawing a picture that follows the logic. As we explained in the previous videos, there are 784 inputs, so that's our input layer. We have 10 output nodes as we one-hot encoded the 10 possible digits. We will work with 2 hidden layers consisting of 50 nodes each. As you may recall, the width and depth of the nets are hyperparameters. I don't know the optimal width and depth for this problem. I surely know that what I've chosen right now is suboptimal. It will be your homework to fine-tune the hyperparameters of our model and obtain improved results from the ones we have in this video. Alright, let's declare 3 variables for the sizes of the shapes. The input size is 784. The output size is 10. And the hidden layer size is 50. The underlying assumption is that all hidden layers are of the same size. That's a simplification quite often adopted in practice. Alternatively, you can create hidden layers with different width, depending on the problem you are trying to solve. Okay, the next line of code is tf.resetDefaultGraph. Essentially, we need this line of code to reset any variables left in memory from previous runs. This is an important thing to do, as the first time we build an algorithm, it is never the best one. Usually, we must play around with hyperparameters to find the ones yielding the optimal result. Therefore, each time we change them, we want to train the model from scratch. This line of code literally means reset the computational graph. The default word here refers to the fact that TensorFlow allows us to define several computational graphs and run them independently as different parts of the training. Throughout our examples, we're not making use of this feature as we declare our variables globally, as part of the default graph that is. Right. Next, we want to declare the placeholders. The lines of code are the same as before, so I won't spend much time on this. Let's get back to our picture. We have the inputs placeholders. To lay down the model, we must define the other 3 layers. They are reached through 3 pairs of weights and biases, 1 for each layer and the activation functions. Let's get on that. This time, we will declare the weights using a different method. tf.get_variable. That's the conventional method to declare variables. It has several advantages, one of them being the default method of initialization related to the method is Xavier. There are 2 required arguments, a name for the variable and its shape. Nothing complicated. I'll call them in the same way as I name the variables. What about size though? The weights have the shape, inputs by outputs for the respective layer. So, for the first weights, we have weights1 equals tf get variable of quotation marks weights1, comma, input size by hidden layer size, and biases1 equals tf get variable of biases1 hidden layer size. The size of the biases equals the number of nodes in the following layer. Simple as that. Alright, let's find the nodes of the first hidden layer. I'll call them outputs 1, so we'll have names consistent with the weights and biases. Time to apply an activation function. I'll go for ReLU, as I know it works well for this problem. But does it really matter? Well, you'll find that out on your own for homework. Let me write this line of code. You'll get it right away. Outputs 1 equals tf NN ReLU of tf matmul inputs weights 1 plus biases 1. Basically, we are applying a ReLU activation to the linear combination of the inputs and weights plus the biases. Nothing new theory-wise. In terms of code, tfNN is a module containing, among other things, the most commonly used activation functions. The activations we have seen are tfNN sigmoid, ton, ReLU, and softmax. Remember that, as you'll need it for the exercises after we are done. Alright, so we have our first hidden layer. Completed analogically, we stack the second one. Weights2 equals tf get variable of weights2 hidden layer size hidden layer size. We can confirm the shape of the weights from our picture. Biases2 equals TF, get variables of. Biases2, hidden layer size. This time, we refer to the number of hidden nodes in the second layer. Finally, outputs2 equals TF_NN, ReLU of TF matmul outputs1 weights 2 plus biases2. Obviously, I chose ReLU again. The multiplication this time is between the hidden nodes from the first hidden layer and weights 2, while the appropriate biases are biases2. Easy. That's how we stack layers. We declare the respective weights and biases, and then we calculate the following outputs. After seeing it once, you can do it on your own. In fact, you will do it on your own if you practice what you've learned. The final weights and biases are declared in the well-known way. The size of weights 3 is the hidden layer size by the output size, while the size of the biases is the output size. This time, we will call the outputs outputs, and we will only calculate their linear combination. Obviously, you can use the same syntax as before and apply an activation function, but I want to show you a little trick we haven't discussed. It is common practice to incorporate the activation of the output layer in the loss. We will see how that's done in our next lecture. Thanks for watching. Okay, we have our outputs. We don't have an activation function. Our familiar module TF_NN contains a function called softmax cross entropy with logits. It basically applies a softmax activation to the output layer and calculates a cross entropy loss function simultaneously. This is a numerically stable function when we deal with very small numbers. Obtaining numbers that are too small jeopardizes our model if we don't deploy this function. I don't know if we need this adjustment for this example, but it is better to be on the safe side. Logits here have a meaning of unscaled probabilities. We expect our output layer to produce probabilities, but before applying softmax, they are unscaled. Softmax fits them into a probability distribution, where they sum up to 1, as we already know. Think about the logits as the outputs before being scaled by softmax. Alright, let's call this variable loss. So, loss is equal to TF_NN softmax cross entropy with logits. We have two arguments, logits and labels. The logits are the outputs. Naturally, the labels are the targets as we are dealing with supervised learning. Alright, we have the loss, but we prefer using the mean loss as it gives a big performance boost, remember? So, let mean loss be equal to TF reduce mean of loss. TF reduce mean is basically the TensorFlow method to find the mean of a tensor. Alright, we have the model and the loss. I want to choose the optimization method. Let me copy the line we used in the intro. This part indicates the optimization method. Last time, it was the gradient descent, but we've gone a long way since then. We mathematically proved the adaptive moment estimation, or ADAM, coupled with batching is a much better alternative. Conveniently enough, the train module contains the ADAM optimizer. I'll just change the function from gradient descent optimizer to ADAM optimizer. I will also set the learning rate at 0.001. Again, that's a hyperparameter that worked well enough, but is not optimal. Play around with it to produce a better result. Alright, that's all we've seen so far. In the next lessons, we will show you how to implement batching, and most important, how to measure the accuracy of the model we've built. Stay tuned, and thanks for watching. Hey! In this lecture, we will introduce something we haven't discussed so far. Prediction accuracy. We just need 2 lines of code, which basically measures in what percentage of the cases the output of the algorithm matched the target. So, for example, in our cat, dog, horse example, the sentence would change to, in what percentage of the cases did the algorithm assign the highest probability to the output that matched the target? So, how do we do this? Let's do another throwback to our cat, dog, horse example, as you know it so well. Let's say we have 4 samples. The left matrix represents our outputs, while the right one, the targets. The targets are 1-hot encoded. Thus, we know that the first photo is of a horse, and the next 3 of cats. According to a model, the first photo has 70% probability of being a horse. We have a match! That's correct. The model recognized the animal. The second photo is of a cat, but the model predicted a dog. The output with the highest probability was the dog class. We have a mismatch. The third and fourth photos were correctly predicted. Overall, our model got 3 of the 4 photos right. Therefore, it has a 75% accuracy. That's the basic logic. So, how should we write this in code? Well, we are only interested in the highest value in a given output row. There is a function called argmax, which is spelled tf argmax, which returns the index of the largest value. What's more, we need the index by columns. As we know the first column is cat, the second one is dog, and third is horse, we can label them 1, 2, 3 or 0, 1, 2, as is the convention in computer science. TF argmax can return just that, the index of the column in which we find the highest argument. So, for the case of our outputs, we will have 2, 1, 0, 0. For our targets, the columns will be 2, 0, 0, 0. If the indices are matching, the model has predicted accurately. Otherwise, it hasn't. It's truly a true-false situation. You are correct, or you aren't. Okay, let's implement that in our problem with some coding. I'll call the variable out equals target. The method that checks if 2 values are equal in TensorFlow is called tf.equal. It returns a boolean, 1 if they match or 0 if they don't. So, tf.equal of. What are we comparing again? The argmax of the outputs and the argmax of the targets. However, to show we only care about the column indices, we include a second argument to the tf argmax function. It is 1, as 1 refers to the column axes. Alright, so out equals target is a vector that contains 0 or 1 for each observation, 1 if it is a match and 0 if it isn't. Then, the accuracy is the mean of that vector. We sum up all the zeros and ones and divide them by their number. We already saw this done through the tf reduce mean method. So, accuracy equals tf reduce mean of out equals target. The out equals target is a boolean though. Depending on the programming language, this might be a problem for calculating the mean. I'll change it to float just in case. The proper method here is tfcast. tfcast has 2 arguments, the object in question and the data type which we want to cast it. Alright. These 2 lines of code will calculate the average training accuracy of the model, which will be a number from 0 to 1. Thanks for watching. Alright, we are almost ready to start learning. Time to prepare the sessions. Once again, ses equals tf.interactive session. Once we've done that, we can initialize the variables. Initializer equals tf global variables initializer, and then we execute through the ses.runInitializer. Okay, nothing new so far. Time for batching. That's something we know theoretically, but haven't done in practice. We are interested in the batch size and the number of batches, right? I would like to remind you that a batch size of 1 equals the stochastic gradient descent, while a batch size equal to the number of samples equals the gradient descent we've seen so far. So, we want a number close to 0, but reasonably high, so it would allow us to preserve the underlying dependencies. I'll set the batch size to 100. That's yet another hyperparameter that you may play with when you fine-tune the algorithm. Okay. The number of batches is equal to the number of samples divided by the batch size. I'll call that variable batches_number, and it will be equal to mnist.train.num examples divided by batch size. We are getting the total number of observations from the mnist tutorial package we imported earlier. Finally, I'll set early stopping mechanisms. The first one is the simplest. I'll put a cap on the maximum number of epochs for which the algorithm will train. I've chosen 15 to be sure I'll finish the training in rational time. The true early stopping will come if the validation loss increases. I'll create a variable that records the validation loss at the previous step. So, prev validation loss. I'll set it to 9,999,999. This is a large number that ensures we don't interrupt the algorithm after the first epoch. Alright, we are all set. In the next lesson, we will make it learn. It is time to execute the loop during which we will optimize the algorithm. The logic is the same as before, but this time, we will have a loop in the loop that goes over the batches during each epoch. As we explained earlier, for each epoch, we will go through several batches and will update the weights multiple times, instead of once per epoch. Let's get to work. For epoch counter in range max epochs, semicolons. The epoch counter is obviously the E from our TensorFlow introduction. The loss for each epoch is a simple average of the loss for each batch. At the beginning of the loop, we want to set the loss to 0. If you are afraid we will lose information, don't worry. All the information is backpropagated to the parameters at the end of each epoch. Okay, let cur epoch loss be equal to 0. It is time for the actual batching. Let's create a second loop inside the big one, which iterates over the training data. So, for batch counter in range batches number, semicolons. Now, we need inputs and targets for each batch. I'll declare input batch, target batch equal to mnist, train, next batch of, batch size. When we imported the mnist dataset, we imported a function that can load data one batch after the other. It is called nextBatch and takes as argument the batch size. For now, that's all you must know. In the business case, we will create classes and functions in Python just to batch. But for now, let's use the readily available ones. Okay, the expression basically loads inputs and targets into the variables input batch and target batch. Right. Now, we use the session run operation, as that's where we optimize and calculate the loss. We do that in the familiar way. We run the optimization and minimize the loss by feeding it with inputs and targets. Or, batch loss equals ses.run of optimize and mean loss, comma, feed dict with input batch as inputs, and target batch as targets. That's the same piece of code we used in our TensorFlow introduction, but for batches. Cool. At the end of each iteration over the batches, we will increase the current epoch loss by the batch loss we just calculated. Let's summarize what this loop does. It loads 100 inputs and 100 targets into the variables input batch and target batch. Then, it optimizes the algorithm and calculates the loss, using these exact 100 samples. Then it records the loss for the iteration. At the next iteration, it loads the next 100 batches, and this is repeated until we go over the whole training dataset. That's the whole learning part. From here on, we will just validate and elaborate on early stopping. Okay. If we run this code, the current epoch loss will contain the sum of the losses over all batches. We can simply find the average loss over the batches by dividing the current loss by the number of batches. Notice this is done outside the batches loop, so inside bigger epoch loop only. That's because we calculate the epoch loss once the training over the batches has been completed. Alright, now the current epoch loss reflects the mean loss, as we wanted. But this mean loss is actually the training loss, right? What about the validation loss? As we know, at the end of every epoch, we validate. Since the optimization for this epoch is over, we can validate. Validation is done by forward propagating the whole validation dataset without optimizing. We simply forward propagate. Let's load in the input batch and target batch the validation samples. We will use the same function, nextBatch, but we will take it from the validation rather than the training dataset. The number of observations is equal to all the validation samples we have. When we forward propagate, we want to record the validation loss and the validation accuracy. This wouldn't be a problem for you if you have completed the exercises in the TensorFlow introduction section. We will record the validation loss and the validation accuracy in two different variables. They are equal to ses.run, mean_loss, accuracy, feed dict input batch as inputs, and target batch as targets. So, calculate the mean loss and the accuracy over the validation dataset and record them in the respective variables. Okay, finally, we want to print the result we've obtained. I won't go through the code thoroughly as it refers to formatting syntax in Python. We want 4 pieces of information: the epoch number, the training loss, the validation loss, and the validation accuracy. The current epoch number is contained in the epoch counter in the bigger loop. The training loss is contained in the cur epoch loss and is the average of the sum of the batch's losses. The validation loss was just completed through forward propagation and is contained in the variable called validation loss. Finally, the validation accuracy was calculated with the validation loss. The formatting is such that we have 3 digits after the loss for the losses and a percentage figure for the accuracy. Okay, are we done? One last detail needs to be addressed. We calculated the validation loss, but we did not set the early stopping mechanism related to it. I'll put a simple if, which breaks the loop when the validation loss is higher than the previous validation loss. We conclude with recording the validation loss in the prev validation loss variable. In this way, we will know when the validation loss starts increasing. Alright, let's go through the big loop. Each iteration from the big loop represents an epoch. At the beginning of each epoch, we set the current training loss to 0. Then we have a different loop for the batches. We iterate over a preset number of batches, all extracted from the training set. Essentially, we utilize the whole training set, but in batches. Therefore, we update the weights and biases as many times as there are batches. At each iteration, we calculate the sum of all batches. When the small loop has ended, we calculate the current epoch loss by dividing the sum of all batch losses by their number to obtain the current epoch loss. We forward propagate the whole validation dataset in a single batch through the optimized model, and we calculate the validation accuracy. Finally, we check if the validation loss is increasing. If not, we carry on with the next epoch. When we reach the maximum number of epochs, or the validation cost starts increasing, the training is over. Clear? Clear. Alright, that's the whole machine learning algorithm. In the next lecture, we will run the code and discuss the results. Thanks for watching. Okay, are you excited? Let's run the code. This is a process that may take a lot of time, sometimes hours. The speed depends on many factors, including the size of the dataset, the number of batches, the width and the depth of the algorithm, and the productivity of the computer you are using. On my computer with these hyperparameters, it took around 20 to 30 seconds to train the model. These are the results. As you can see, the training was completed in 8 epochs. This shows the validation loss started increasing and the early stopping mechanism was triggered. In other words, the model started overfitting. What about the losses? The training loss acted as usual. It was constantly decreasing. The validation loss was moving accordingly until the last epoch, when it increased. What we care about, though, is the algorithm's accuracy. After the first epoch, we achieved 93% accuracy. This is a good model already. It may be surprising that the model was so accurate even at the first epoch. But in fact, there were several hundred batches that optimized the algorithm before the end of that epoch. That's the strength of batching. It is much, much faster and still accomplishes amazing results. What happened later is that the accuracy started improving, but in a declining manner. It jumped from 93% to 95%, and then gained less than 0.5% per epoch. Finally, we got a validation accuracy of around 97%. Let's see what happens if I change one of the hyperparameters. I'll fine-tune the number of hidden nodes as it is one of the easiest to amend. Let's change the hidden layer size from 50 to 100 and run the code once more. The old parameters are forgotten due to the line of code we added earlier. Let's check the new results. We see that, with 100 nodes in each hidden layer, we have dramatically increased the accuracy of the model. Around the 4th epoch, we had reached the result from the last run. This time, the final validation accuracy got up to around 97.5%. Okay, cool. Does that mean we got an accuracy of 97.5%? If I'm asking, that's obviously a tricky question. No, it doesn't. That's the validation accuracy. We still must test the model on the test dataset. The final accuracy of the model comes from forward propagating through the test dataset, not the validation, as we may overfit. But didn't we already deal with overfitting? That's a fine point, as some of you could miss the difference between validation and test datasets. Let's clarify that. We train on the training dataset and then validate on the validation data. In this way, we make sure our parameters, the weights and biases, don't overfit. Once we train our first model though, we fiddle with the hyperparameters. Normally, we won't change only the width of the hidden layers. We can adjust the depth, the learning rate, the batch size, the activation functions for each layer, and so on. Each time we make a change, we run the model once more and check if the validation accuracy improved. After 10 to 20 different combinations, we may reach a model with outstanding validation accuracy. So, we try to find the best hyperparameters. But these are not the best hyperparameters. These are the hyperparameters that fit the validation dataset best. Essentially, we are overfitting the hyperparameters. That's why we need the test. It is a dataset the model has truly never seen. We don't train the parameters on the validation dataset, but we adjust our model considering the results from the validation. With that in mind, validation is not the best instance for accuracy. Okay, let's test the model. We'll need to forward propagate and print out the accuracy, following the logic we used so far. This time, the data comes from the test dataset. Here's our test accuracy. It obviously differs from the validation one. It could be an improvement, or it could be worse. Doesn't matter. What's important is this is the final accuracy of our algorithm. Once we test, we are not allowed, at least conceptually, to change the model, considering the test accuracy. If we do that, we are overfitting the hyperparameters to the test, which defeats the purpose of the separation between validation and test datasets. Okay, that's about it. Our model has a final test accuracy around 97.5%. Take a moment to appreciate this result. Imagine someone came to you a month ago and told you, here are 70,000 photos of handwritten squiggly blotched crooked digits. Write an algorithm that recognizes which digit has been written. What would you think about that? Probably, you wouldn't know where to start. Now, with just a few lines of code, we've written an algorithm that gets 97 to 98 out of 100 digits right. This is remarkable accuracy, remembering the simple model we used. I'd like to conclude with the take of TensorFlow.org on the MNIST training. They show a model with an accuracy of 92% and ask, is that good? Their answer is, not really. In fact, it's pretty bad. Our model was a bit more complicated than the one they show, and we achieved an accuracy of 97.5%. The question is, can you do better? Check the next lecture for instructions on how to do that for homework. Thanks for watching.
The opportunity to take you through the business case. In a way, this is the peak of the course, but it is simply the application of everything you already know. Here's the problem. You are given data from an audiobook app. Logically, it relates to the audio version of books only. Each customer in the database has made a purchase at least once. That's the condition to be included. We want to create a machine learning algorithm based on our data that can predict if a customer will buy again from the audiobook company. The main idea is that the company shouldn't spend its advertising budget targeting individuals who are unlikely to come back. If we can focus our efforts on customers likely to convert again, we can obtain improved sales and profitability figures. So, our model will take several metrics and will try to predict human behavior. A side effect of our study is that the model will show us which are the most important metrics for a customer to come back. Having the data and the technology to identify prospective customers creates a lot of value and growth opportunities. It is one of the better applications of data science. All right, here's our data. This CSV file is included in the lecture resources. When you download it, the column headers won't be included, as we want no text in the data when training the model. Each row represents a person. Let's go through the columns and see why each one of them could be of use. First, we have customer ID. Here, ID is like a name. Whether the ID is 1, 2, 3, or John 1, John 2, John 3 makes no difference. As no information is contained in the ID, we will skip it in our algorithm. Okay, next we have book length. The overall book length is the sum of the lengths of all purchases. We also have the average book length. The average book length is basically the sum divided by the number of purchases. So, if somebody has bought a single audiobook, the average length and the overall length for this person will be equal. All right. There is no need to include the number of purchases, as it is contained in the two variables we just described. Then we have the overall price paid and the average price paid. These variables were constructed in the same way as those for book length. The price is in dollars, although it makes no difference to the algorithm. By the way, the price variable is almost always a good predictor of behavior. The next variable is review. Review is a Boolean. It shows if the customer left a review. This is a metric that shows engagement with the platform. Our assumption is that people who leave reviews are more likely to convert again. Then we have review out of 10. This is a different variable. It measures the review of a customer on a scale from 1 to 10. Pay attention here, as we will show you the first pre-processing trick. Here it comes. Logically, we will only have a value for people who left a review. By examining the table, we quickly see most people leave no review, as in most marketplaces. That's bad for our dataset and bad in general. Side note, if you like our course, don't forget to leave a review. Just saying. We have decided to leave the reviews posted to the platform and substitute all missing values with the average review. The average is 8.91. For our machine learning algorithm, 8.91 would mean the status quo. A review bigger than 8.91 would indicate above average feelings, while a review less than 8.91 would indicate below average feelings. Notice I am saying feelings. Review is yet another variable that is an average. A customer may have bought 2 or 3 books on the platform. The average review she left indicates her feelings towards the content on the medium or better, the medium as a whole. An average of 2 out of 10 indicates the person did not have a pleasant experience with audiobooks, especially when the average is 8.91. It is logical that such a customer is not likely to buy again. All right, done here. Then we have total minutes listened, which is a measure of engagement. Next to it, we have completion. Completion is the total minutes listened divided by the total length of books a person has purchased, assuming people don't re-listen to books. Both variables are self-explanatory. The next variable is support requests. It is numerical and shows the total number of support requests a person has opened. Support is anything from forgotten password to assistance on using the platform. Once more, this is a measure of engagement. It may turn out that the more support a person needed, the more he or she got fed up with the platform and abandoned it. Or he or she likes it so much that by using it, stumbles upon different issues, unlike someone who never opens the app. Finally, we have a variable measuring the difference between the last time a person interacted with the platform and their first purchase date. That's yet another measure of engagement. The bigger the difference, the better. If a person engages regularly with the platform, this difference will be bigger. Thus, the customer is likely to convert again. If the value of this variable is 0, we are sure the customer has never accessed what he has bought. Or perhaps he did it on the first day only, so it is unlikely he or she will convert again. All right, these are our inputs. It is always necessary to ask how the data was gathered. This piece of information is valuable for any analysis. The data was gathered from the audiobook app, as we said. It represents 2 years' worth of engagement. Now, we are doing supervised learning, so we need targets, right? The targets will be a Boolean. 1 if a person converted, and 0 if he or she didn't. But what does it mean to convert? That's the big question here. We have taken an extra 6 months of data after the 2-year period to check if a user converted. So, we took 2 years and 6 months of data. The first 2 years are contained in the data set you have here. The next 6 months will show us if a person converted. In other words, if he or she bought another book. And if that happened, we can count them as a conversion, and the target will be 1. Otherwise, it is 0. That's how we created the targets column. 6 months sounded reasonable enough for us. If one buys no new audiobook in that period, chances are they've gone to a competitor or didn't like the audiobook way of digesting information. Okay. That said, our task is simple. Create a machine learning algorithm that can predict if a customer will buy again. This is a classification problem with 2 classes, won't buy and will buy, represented by 0s and 1s. In the next lesson, we will outline the solution. You can try solving the problem on your own or check out the next few lessons. Thanks for watching. We know what we are supposed to do. Let's see how we will do it. Since we are working with real-life data, we must pre-process it. Pre-processing is important for machine learning. In a data science team, there may be a person whose sole job is to prepare datasets for analysis. This is why we would like to show you a couple of common techniques here. To create a machine learning algorithm from scratch, we need 3 important steps. The first one is to balance the dataset. We will explain that in a separate lecture as it needs extra attention. The second step is to divide the dataset into 3 parts: training, validation, and test. We already know why we must do it. Now we will see how to do it from scratch. Finally, we will save the newly created sets in a tensor-friendly format, the good old NPZ. Once we've done that, we will create a class that handles batching. This part of the code will be all about programming. Once you have the code, you'll be able to reuse it. Consider it a template for future use. In the MNIST example, we use the TensorFlow data provider for both pre-processing and batching. This time, we will do it on our own. Finally, we will create the machine learning algorithm. The code is 90% the same as the one in the MNIST example. Here's the true power of TensorFlow. We will use the same structure to create a different model, which will be equally powerful. By the end, you can take any dataset and repeat this operation using the code to create deep neural networks for countless problems. Ready? Okay, see you in the next video. Before we start pre-processing, I'll take a minute to talk about the importance of balancing your dataset. Let's think about a photo classification problem with 2 classes, cats and dogs. What accuracy do you expect from a good model? Well, if we correctly classify 70% of the photos, that's not too bad. 80% accuracy is good, while 90% is very good for beginners, right? I'm not talking about Google and Facebook classifications, which achieve 99.99% accuracy. 90% accuracy for most problems is an impressive accomplishment. Okay, now imagine a model that takes animal photos and outputs only cats. No matter what you feed to the algorithm, it will always output cat as the answer. A bad model, isn't it? Is this machine learning, you may ask? It's definitely not the result we want from a machine learning algorithm, but is a common result. Imagine that in our data set, 90% of the photos are of cats and 10% dogs. The same awfully bad model applied to this data set would classify all photos as cats. But 90% of the photos in that data set are cats. What's the accuracy of the algorithm? It is 90%. Incredible! Why does this problem arise? Well, since the machine learning algorithm tries to optimize the loss, it quickly realizes that if so many targets are cats, the output should most likely be cats to achieve a great result. And therefore, it comes up with the same prediction at all times. Cats. Okay. Now, if the distribution of photos is 90% cats and 10% dogs, a model with an 80% accuracy is a bad model. Why? Because the dumb model that outputs only cats will do better than it. Therefore, only a result above 90% is a more favorable one. We refer to the initial probability of picking a photo of some class as a prior. The priors are 0.9 for cats and 0.1 for dogs. The priors are balanced when 50% of the photos are cats and 50% are dogs, or 0.5 and 0.5. Examples of unbalanced priors are 0.9 and 0.1, 0.7 and 0.3, 0.6 and 0.4, and so on. Each pair is prone to the issue discussed a minute ago. A machine learning algorithm may quickly learn that one class is much more common than the other and decide always to output the value with the higher prior. Okay, if we have 3 classes, cats, dogs, and horses, balancing the dataset would imply picking a dataset where each class amounts to approximately 1/3 of the dataset. If we have 4 classes, 25% each. You get the gist. In our business case, by exploring the targets, we quickly realize most customers did not convert in the given time span. We must surely balance the dataset to proceed. That's done by counting the total number of target ones and matching the same number of zeros to them. All right, we'll do that in the next lecture. See you there. Let's start pre-processing. I won't dive into the code too much, as we want to focus on machine learning as much as possible. You can later examine the code with comments or ask a question in the Q&A section to get a better understanding. As usual, I'll import NumPy as NP. Next, from Scikit-learn, I'll import pre-processing. Let me stop for a second. I'll use the Scikit-learn capabilities for standardizing the inputs. It's one line of code, which drastically improves the accuracy of the model. Almost always, we standardize all inputs as the quality of the algorithm improves significantly. Without standardizing the inputs, we reach 10% less accuracy for the model we will build here. And you remember how a 0.5% improvement in the MNIST example was a great success. We suggested installing Scikit-learn when we were setting up the environment in the 3rd section of the course. It was also one of the exercises. If you don't have it installed yet, I suggest installing the package following the well-known methodology. Let's get to work. First, I'll load the CSV file. So, raw CSV data equals np load.txt audiobooksdata.csv with a comma delimiter. Okay, now we have the data in a variable. Our inputs are all the variables in the CSV except for the first and the last column. The first column is the arbitrarily chosen ID, while the last is the targets. Let's put that in a new variable called unscaled inputs all, which takes all columns, excluding the ID and the targets. So, the 0th column and the last one, or minus first. Let's record the targets in the variable targetsAll using the same method. They are the last column of the CSV. Cool! We have extracted the inputs and the targets. The next section of code will deal with balancing the dataset. We will count the number of targets that are ones, as we know they are less than the zeros. Next, we will keep as many zeros as there are ones. Okay, let's count the targets that are ones. If we sum all targets, which can take only 0 and 1 as value, we will get the number of targets that are ones. So, number of 1 targets is equal to NP, sum of targetsAll. I'll declare it as an integer, as targetsAll may be a Boolean, depending on the programming language. Then, I'll just keep as many zeros as ones. Let's set a counter for the 0 targets equal to 0. Next, we will need a variable that records the indices to be removed. For now, it is empty, but we want it to be a list or a tuple, so we put empty brackets. Let's iterate over the dataset and balance it. For I in range targetsAll dot shape0 semicolons. TargetsAll contained. All targets. Its shape on the 0 axis is basically the length of the vector, so it will show us the number of all targets. In the loop, we want to increase the counter by 1 if the target at position I is 0. In that same if, we put another if, which will add an index to the variable indices to remove, if the zero's counter is over the number of ones. I'll use the append method, which simply adds an element to a list. So, after the counter for zeros matches the number of ones, I'll note all indices to be removed. Okay, so after we run the code, the variable indices to remove will contain the indices of all targets we won't need. Deleting these entries will balance the dataset. Okay, let's create a new variable. Unscaled inputs with equal priors, which is equal to np delete of unscaled inputs all, from which I want to delete the entries with indices from indices to remove on axis 0 of the vector. Similarly, the targets with equal priors are equal to np delete of targetsAll indices to remove on axis 0. Done. All right, we have a balanced dataset. Next, we want to standardize or scale the inputs. The inputs are currently unscaled, and we noted that standardizing them will greatly improve the algorithm. A simple line of code takes care of that. Scaled inputs is equal to preprocessing dot scale of unscaled inputs equal priors. That's the preprocessing library we imported from Scikit-learn. The scale method standardizes the dataset along each variable. So basically, all inputs will be standardized. Cool! So, we have a balanced dataset, which is also scaled. Our preprocessing is almost finished. A little trick is to shuffle the inputs and the targets. We are basically keeping the same information, but in a different order. It's possible that the original dataset was collected in the order of date. Since we will be batching, we must shuffle the data. It should be as randomly spread as possible so batching works fine. Let me provide a counterexample. Imagine the data is ordered, so each batch represents approximately a different day of purchases. Inside the batch, the data is homogeneous, while between batches, it is very heterogeneous due to promotions, day-of-the-week effects, and so on. This will confuse the stochastic gradient descent when we average the loss across batches. Overall, we want them shuffled. Let's see the code. First, we take the indices from the axis 0 of the scaled inputs shape and place them in a variable. Then we use the NP random shuffle method to shuffle them. Finally, we create shuffled inputs and shuffled targets variables equal to the scaled inputs and the targets, where the indices are the shuffled indices. All right. So far, we have pre-processed the data, shuffled it, and balanced the dataset. What we have left is to split it into training, validation, and test. Let's count the total number of samples. It is equal to the shape of the shuffled inputs on the 0th axis. Next, we must determine the size of the 3 datasets. I'll use the 80-10-10 split. Trained samples count is equal to 0.8 times the total number of samples. Naturally, we want to make sure the number is an integer. Next, the validation samples count is 0.1 times the total number of samples. Finally, the test samples count is equal to the total number of samples minus the training and the validation. Cool. We have the sizes of the train, validation, and test. Let's extract them from the big dataset. The train inputs are given by the first train samples count of the pre-processed inputs. The train targets are the first train samples count of the targets. Analogically, the validation inputs are the inputs in the interval from train samples count to train samples count plus validation samples count. The validation targets are the targets in the same interval. Finally, the test is everything that is left. Cool! We have split the dataset into training, validation, and test. It is useful to check if we have balanced the dataset. Moreover, we may have balanced the whole dataset, but not the training, validation, and test sets. I'll print the number of ones for each dataset, the total number of samples, and the proportion of ones as a part of the total. They should all be around 50%. Let's quickly run that code. We can see the training set is considerably larger than the validation and the test. This is how we wanted it to be. The total number of observations is around 4,500, which is a relatively good amount of data, although we started with around 15,000 samples in the CSV. The proportions, or should I say the priors, look okay, as they are almost 50%. Note that 52% or 55% for 2 classes are also fine. However, we want to be as close to 50% as possible. Okay. Finally, we save the 3 datasets using the NP saves method. I name them in a very semantic way, so we can easily use them later. All right, our data is pre-processed now. Each time we run the code, we will get different proportions as we shuffle the indices randomly, so training, validation, and test datasets will contain different samples. You can use this same code to pre-process any dataset where you have 2 classes. The code will skip the first column of the data, as here we skip the ID, and the last column will be treated as targets. If you want to customize the code for a problem with more classes, you must balance the dataset classes instead of 2. Everything else should be the same. The pre-processing is over. Henceforth, we will only work with the NPZ files. I will save this Jupyter Notebook and continue with the machine learning in a separate one. Make sure that you have the raw CSV when you run the code on your computer. In this way, you will create the NPZ files, which we will use for the machine learning part. There are some additional adjustments you can make the code to improve the pre-processing. Check out the exercises and work on them if you'd like. Great work! Next time, we will take care of batching. Thanks for watching. In this lesson, we will create a class that will handle batching for us. You can perform batching without a class, but that's the clean way to do it in IT jargon. As with the pre-processing part, we have written the code in an extremely reusable way. You can use it as a template for future projects if you want to. What you'll see in this lecture is more programming than machine learning. We will go through the code, but not in depth. I'll only stress the points you must change when reusing the code. All right. Here's the whole code with comments. First, I'll import NumPy as NP as I don't have the package in this notebook. Then I'll create a class called Audiobooks Data Reader. There are 3 functions in the class: init, next, and iter. This class will be an iterator. An iterator in Python is a class with methods next and iter and is used with loops. Let's see how. So far, we use loops that iterate for a number of observations, like for e in range 100, or for epoch counter in range max epochs. We can instead use an iterator and write for input in data, where data is an instance of the class. Then we proceed as usual and include the operations we want the loop to perform. With batching, we want to take batches one after the other and calculate the loss for each one. So, a sample code would be for input batch, target batch in train_data, calculate the loss. Train data will be an instance of the class. So basically, we will take input batches and target batches from the class until the data in the train_data object is exhausted. At each iteration, we will calculate the loss for each batch, as we did with the MNIST. Okay, let's look at the class. Remember, it is all about batching. The init method loads the data from the NPZ. The next method loads the next batch from the NPZ. Finally, the iter tells Python that the class is iterable. Knowing this, once a variable is an instance of the class, when included in a loop, it will load the first batch, then iterate over the dataset, taking one batch after the other until the dataset is exhausted. Let's start from the first method. The first method has 2 arguments, dataset and batch size. The self one is simply Python notation that defines the method as an instance method, as opposed to a static method. For those of you who are not familiar with this notion, it is really simple. Imagine you have a class, person, and an object that is instance of this class, Alice. A static method, say hi, defined without self would be called as person.sayHi parentheses. One defined with self would be called as Alice.sayHi parentheses. So, the difference between writing self or not is whether the method will be assigned to instances of the class or to the class itself. Back to our method, it has only 2 real arguments, dataset and batch size. The batch size is an optional argument. If we don't include it when calling the class will assume it has to load all the data as a single batch. For example, if I declare a variable x, which is an instance of the class, with arguments train and 5, the result would be to load the train dataset and then proceed with the operations, taking batches of 5 samples at a time. If I declare a different variable y, which is an instance of the class, with a single argument, validation, the result would be to load the validation dataset, where the whole data is contained in a single batch. We will need that when we forward propagate the validation and test datasets, as they need not be batched. Okay, for this class to work, the names of the datasets must be coherent. As you can see, we called them audiobooks data. Train, validation, and test formatted in the same way. Whenever you want to reuse the code, simply change this part to whatever suits your problem. All right, the next 2 methods load the next batch and show the class as an iterator. The next function slices the next batch out of the dataset and loads it for the next iteration. In addition, this is the place where we one-hot encode the targets. As the targets were 0s and 1s, we want to split them into one-hot encoded targets. So 0 ones and 1 zeros. We have used a parameter called classesNumber. There are two classes, zeros and ones. If you have a classification problem with more than two classes, then you should change the class num variable accordingly. The functions return the inputs batch and the one-hot encoded targets. This is the only output we have associated with this class. Therefore, our earlier example, for input batch, target batch in train data, basically means we take the input and target batches from this return operation. All right, that's about all we need to know. Let's summarize. This class lets us do the batching in a fast and efficient way. We can reuse the code for any problem that requires batching. The changes we should make for a different classification problem are: 1. Adjust the names of the NPZ files. 2. Adjust the number of classes. That's all. In the next lesson, we will create our machine learning algorithm. It will be an interesting one. Thanks for watching. All right, it's high time to crack the business case. Let's start by taking a look at the net we are going to deal with. We have an input layer consisting of 10 units. Those are the inputs from our CSV. There are only two output nodes as there are only two possibilities, 0 and 1. We will build a net with two hidden layers. The number of units in each layer will be 50, but as we know very well, this is extremely easy to amend. Therefore, for a prototype of an algorithm, 50 is a good value. 50 hidden units in the hidden layers provide enough complexity that we expect the algorithm to be much more sophisticated than, say, a linear or logistic regression. At the same time, we don't want to put too many units initially, as we want to complete the learning quite fast and see if anything is being learned at all. All right, let's start coding. The first thing we need to do is to import TensorFlow. We didn't need it so far, so we did not import it. Cool. Throughout the entire course, we claim TensorFlow code is extremely reusable. We will now prove that is in fact true. Let me copy the MNIST model until the epoch loop. I am sure you are already familiar with this code. We are going to need a couple of adjustments. First, we know that our input size is 10 and not 784. The output size is 2 instead of 10. As we discussed a few seconds ago, I will leave the hidden layer size at 50. Then we have our good old reset default graph method, which will let us train the model from scratch simply by rerunning the cell. All right. Then we have the placeholders containing inputs and targets. I will change the targets type of data to int32 because the targets are zeros and ones. They are integers, and it makes sense to declare them as such. Keeping them as floats should work perfectly fine too, but it just doesn't seem right to me. Okay. The model itself is exactly the same. Everything is parameterized, so no adjustments are needed. There are two hidden layers, as in the MNIST, and an output layer, which is reached through a simple linear combination. The activation function of both hidden layers is ReLU, while the activation function for the output layer is incorporated in the loss through the softmax cross entropy with logits loss. Then we find the mean loss using the reduceMean method. The next two lines of code define the accuracy variable. They remain unchanged and serve the same purpose as before. The optimization will happen using the Atom optimizer with a learning rate of 0.001. Note that, once again, we are building a model with suboptimal hyperparameters, and it will be up to you to fine-tune it later on. All right. After declaring the interactive session and the initializer, we prepare for initializing the variables. We will keep the batch size at 100. This time, though, we don't need the batch's number. Remember that we incorporated it in the class. The class takes care of batching. It just needed the batch size. So, I'll remove the corresponding line of code. Similarly, the early stopping mechanisms may remain the same. I'll change the max number of epochs to 50, as I already know how the algorithm will behave, and 50 is a better cap. Cool. We didn't need to change much. And trust me, this will yield a great model. Take a moment to appreciate how we're reusing 99% of the code for entirely different problems: digit recognition and customer conversion. This is the incredible advantage of using frameworks like TensorFlow. Time for the first major difference. In one of our first lectures, we said that around this time we would normally load the data. In the MNIST example, we use the TensorFlow data provider. Here, though, we pre-process the data on our own, so we will need to use the tools we developed to load the data. Let's declare two variables: train data and validation data. They will both be instances of the audiobook's data reader class. Train data equals audiobook's data reader with two arguments, train and batch size. So, train data is an instance of the audiobook's data reader class. Let me scroll up to the class. The train data variable we called was just loaded with the data from audiobooks data train.npz. It will take 100 samples at a time, as the batch size is 100. All right. Analogically, validation data equals audiobook's data reader with argument validation. We are all set. We can now create the loops that will train our algorithm. See you in the next lecture. Thanks for watching. Okay, we are almost done. I'll write some parts of the loop manually, as there will be a couple of new things we want to show you. As before, for epoch counter in range max epochs, semicolons. We start by setting the current epoch loss to 0. Next, we will create the loop which will iterate over the training data. As we explained in the lecture about the class, since the class is iterable, we can simply write for input batch, target batch in train data, semicolons. In this way, we will take input batches and target batches from the train data 100 samples at a time, until we have gone through the whole training dataset. Being able to do that in such a concise fashion was more or less the purpose of the class we created. Excellent! The next piece of code is the same as before. We will run the optimization step and would obtain the mean loss by feeding inputs from the input batch and targets from the target batch. At the end of the loop, we will add the batch loss to the current epoch loss, as before. That's the whole loop. The only difference is that we used our own data provider, which we created in the class lecture, instead of the MNIST data provider. All right. Next, we will have to calculate the mean current epoch loss. It is equal to the current epoch loss variable divided by the number of batches. We get the number of batches from the train data object. Going back to the class, we see that there is an attribute taking care of that. Okay, that was the training part. Notice that everything is as parameterized as possible. This loop won't need to be adjusted in any way when you want to reuse it. All right, time to validate. I'll set the validation loss and the validation accuracy for the epoch to 0. How are we going to approach the problem? Like true programmers, right? We will copy-paste our training batch code and adjust it where needed. So, what are the changes? For input batch, target batch in train data will change to validation data. Then, we want to fetch the loss and the accuracy by running the mean loss and the accuracy operations. We'll feed the inputs and the targets from the input batch and the target batch respectively. I'll record the values directly in validation loss and validation accuracy. As we said before, our data provider was created in a way that would load the validation and test dataset in a single batch, while the training data in many batches. Moreover, the optimize operation is now absent, so we will simply forward propagate the whole validation dataset through the net. You may wonder why we need a loop. We are using it since our class was an iterator. Logically, this loop will always have a single iteration. Using a loop won't affect the speed of the algorithm and is much easier to grasp because of the similarities with the training loop. Cool. Finally, I'll copy and paste everything else we had in the MNIST example. We have the statistics for each epoch, which remain unchanged. Then we have an if statement, which triggers early stopping by breaking the loop if the validation loss starts increasing. Finally, we record the current validation loss in the previous validation loss variable. That's all. Let's go over the process. We create a loop for the epochs. It iterates until we have reached the maximum number of epochs. Next, we set the current loss to 0. We train the model in batches until the data in train data is exhausted. We optimize the mean loss by feeding the algorithm with data from train data in batches. We record the sum of all batch losses. When training is completed, we will find the epoch loss by dividing the sum of the batch losses by their number. After the training comes the validation. We set the validation loss and the validation accuracy to 0. We forward propagate using the same class but with a single batch. The validation loop iterates only once. We directly record the validation loss and accuracy in the respective variables. At the end of each epoch, we print the statistics, which are formatted in an easily readable way. Finally, we check if the validation loss is increasing and trigger early stopping if needed. That's the whole code. Our next lecture is going to be an exciting one, as we will run the code we have prepared. Thanks for watching. All right, let's run the code. With your extensive knowledge, you can easily interpret the result. I won't spend much time on that. There are several other points I want to stress, and they are all conceptual rather than quantitative. First, the final validation accuracy of the model is 80%. The priors were 50%, so our machine learning algorithm definitely learned a lot. It managed to classify around 80% of the customers correctly. So, if we are given 5 customers and their audiobook activity, we will be able to correctly identify future customer behavior of 4 of them. What does this mean for us? We can use this information for what we intended to. We can focus our marketing efforts only on those customers who are likely to convert again. Think about this amazing discovery. At the beginning, we started with a bunch of raw data, which did not make a whole lot of sense to anyone who is not in this line of business. Moreover, many variables were binary and there were lots of missing values. Even the orders of magnitude had nothing in common. If we were to manually explore the data and give an educated guess on whether a customer would convert again, it is likely that the result would be as good as blind guessing. My personal bet is that a human would do even worse than the prior. With some descriptive statistics and regression models, we would get a better result. But I assure you, it wouldn't be very impressive. And you would definitely need a lot more than the 30 minutes we spent in order to create this model. It is extremely hard to predict human behavior, and most of the time it is even counterintuitive. However, the machine learning algorithm we created here is a new tool in your arsenal that has given you an incredible edge and a skill that is easily applicable in any business out there. You leverage the power of artificial intelligence to reach a business intelligence insight. Congratulations and great work! As you can see, we are separating the tests in a different lecture. That's because we want to encourage you to do it on your own as homework. If you want to try that, please pause the video, download the file associated with the lesson, and go for it. If not, you can proceed with the lecture. We load the test dataset in the variable testData using the same methodology as the one for the validation data. So, testData equals audiobooks data reader of test. In order to test the model, we need to forward propagate the test data through the net. Let's copy and paste the code from the forward propagation of the validation data. We are iterating in the test data, so I'll change that. Then, we simply need the accuracy, so I'll delete the loss and we'll record the output we obtain in a variable called test accuracy. Done! The test accuracy in percentage points is given by the test accuracy variable times 100. However, when we run a single output with ses.run, it is a list rather than a float. In this case, the test accuracy is a list with a single value, the one we obtain from forward propagation. In order to perform the multiplication, we need to take the only item in that list, which is the value of position 0. All right. Finally, we print the test accuracy. Let's run the code. Once again, that's the final accuracy of the model. Naturally, it is close to the validation one, as we did not fiddle too much with hyperparameters. From this point on, I am no longer allowed to change the model. I'll follow this simple machine learning rule and let you do the hard work. There are several exercises waiting for you. Please go ahead and give them a go. Good luck, and thanks for watching. So far, we've given you a bit of homework on the pre-processing part. In this lecture, we will give you some more. You have plenty of room for fine-tuning, as in our previous videos we simply reuse the MNIST structure. However, we don't have the data to reach an outstanding accuracy, like in the MNIST. We will give you some guidelines, but don't get discouraged if you can't get above 85% accuracy. Sometimes you have the best tools, but insufficient data. You will achieve the biggest improvement when adjusting the width and depth of the algorithm. I would like to leave a note here. Many problems may be solved by simply increasing the width and depth of the algorithm. There are some extremely deep nets with hundreds or even thousands of hidden layers. Our data is not as complex, but it may be worth it to practice your TensorFlow skills by creating 5 or even 10 hidden layers. Similarly, the number of hidden units can be increased to 1,000 or 10,000. However, both the width and the depth are very computationally expensive. I don't recommend you increase the hidden layer size to 10,000 on your home computer. If you increase the depth too much, even let's say 100 hidden units, may cause your computer to freeze. The next thing we can focus on are activation functions. Think about their graphs and how they would change the data. For example, a ReLU activation at the first layer would cause many hidden units to be zeroed because of the way it behaves. This may prove problematic, as you may make many nodes useless. However, in the MNIST problem, that was exactly what we needed, to clear up the inputs. What about the softmax? Quite often, the softmax is the activation function for the output layer, but we don't want to include it in the hidden layers before that. That's because it would scale all inputs in the previous layer to probabilities. Moreover, it would do so relative to the other inputs rather than independently. It is possible to lose a great amount of information about the variability of the data. Thus, you must be careful with it. Next, you can fiddle with the batch size. A batch size of 1 equals the stochastic gradient descent. It will cause the algorithm to learn quite quickly, but not so accurately. You should try applying batch sizes that will likely preserve underlying dependencies. In addition, you can also experiment with the learning rate, although that may not be as fruitful, as Atom adapts it dynamically. What you can do is visit the TensorFlow website and check out other optimizers comparing their performance to that of Atom for your specific problem. Alternatively, you should be able to go to the module tf.contrib. That's where the TensorFlow community contributes to the framework. You may find quite interesting methods that are not part of the core TensorFlow framework. There are really a ton of resources available out there. Finally, I encourage you to take your own data and try to implement this methodology in order to solve a given problem. If you don't know where to start, Kaggle is a great place to search through datasets. Moreover, a lot of people share their own code, so you can see how they approach the same problem you tried. Some people will use TensorFlow, others will be bet on Scikit-learn. In any case, you will surely find people with a machine learning level similar to yours. Okay, let's wrap it up here. This was our real-life business case example. Thanks for watching. So, what's further out there in terms of machine learning? Now that you've completed this course, you've developed a solid understanding of how neural networks work. Unknowingly, you have also acquired a ton of machine learning knowledge and skills that are applicable to non-neural network machine learning approaches. This course was the important foundation that now allows you to move on to other branches of this cutting-edge technology. Do you remember the examples of machine learning given in the very first lecture? Self-driving cars, facial recognition, smart assistants like Siri? Well, the bad news is that you are not ready to understand exactly how they work right away. The good news is, however, that you now know everything necessary to start doing that. Even better news is that working on business cases like the one we explored would not require techniques like facial recognition or natural language processing. In fact, only a handful of companies around the world create cutting-edge technologies like Siri. However, most large, self-respectable entities have a data science division analyzing their business data, and that's where you can fit in. In any case, how are the problems of self-driving cars, facial recognition, and smart assistants approached? There are two big extensions on top of neural networks these systems use: convolutional neural networks, or CNNs, and recurrent neural networks, or RNNs. We are planning on furthering this topic into CNNs and RNNs, which is why we made two separate lectures looking into each of them. But be sure, the knowledge you've acquired so far will be 100% relevant when studying these topics. We'll discuss more about CNNs and RNNs in our next lectures. Thanks for watching. In this lesson, we will look into convolutional neural networks. You're already familiar with the MNIST dataset, so it will be easier to describe a typical CNN. In our approach, which was simply feed-forward neural networks, we flattened the images into a vector of length 784. That way, however, we lost the spatial information of every pixel's neighborhood of pixels. For example, the 28th pixel and the 29th pixel in the vector we use are next to each other in the vector, right? Well, in the picture, they are actually quite far away. Furthermore, since we always start by taking a linear combination of the inputs, it will search for particular digits in particular places. For instance, a 7 written in the top left corner is very different from a 7 written in the bottom right corner. A convolutional neural network solves this problem by dealing with the original 28 by 28 photos without flattening them. Instead, it applies tiny, say 5 by 5 so-called kernels to every possible position of the image. Kernels are like weights. So, if we start from the top and continue down, we can count a total of 24 5 by 5 squares. The same applies if we go from the left to the right side. Therefore, the next layer is 24 by 24, which is the number of 5 by 5 submatrices. This is called convolution. The layer that we get is called a convolutional layer. The number of kernels you choose is a hyperparameter, and you are not restricted to a single kernel. Apart from convolution, there is another main step in CNNs: pooling. Most commonly, we would divide these 24 by 24 squares into multiple 2 by 2 squares without overlapping, and we'll take the largest number in the 2 by 2 matrix because we assume it is the strongest detail. That's how we reduce the dimensionality of the problem. What makes the issue slightly more complicated, though, is that most photos have colors, which implies that images have height and width, but also color or depth. This is a third dimension with 3 variables according to the RGB scheme: red, green, and blue. Thus, our original photo was not of shape 28 by 28, but rather 28 by 28 by 3. That's also where the whole tensor approach fits perfectly. So, the initial 28 by 28 matrix was not reduced to 24 by 24, but was actually converted in a 28 by 28 by 3 tensor, which was then reduced to a 24 by 24 by 3 plus tensor, depending on the number of kernels we chose to use. If we convolute and pool for long enough, we can reduce the dimensions to a vector containing one-hot encoded categories, like dog, cat, horse, and so on. In order to truly get CNNs, we need much more time than a couple of minutes. In general, though, to get the gist of it, CNNs are mainly used in image recognition due to their two major advantages. Spatial proximities are preserved. It matters where in the photo we find a certain detail. And a certain detail such as a human eye is looked for everywhere in the photo. Thus, a face can be recognized everywhere on the image. These two advantages make CNN's predictive power much higher than that of NNs, especially when it comes to image-related problems. Instances are robot vision, self-driving cars, Facebook tagging, and Apple's face recognition for unlocking the iPhone. A recent application of CNNs for a non-image related problem was the Google Assistant technology developed by DeepMind. This is a competitor product to Siri, Alexa, and Cortana. Allegedly, they managed to apply CNNs in a way that converts artificial sound in a more human-like shape than ever. You can find the original announcement by DeepMind in the course resources. Alright, how likely is it that you'll use CNNs? Well, currently, image-related problems are mostly used by companies such as Google, Tesla, Apple, Microsoft, Amazon, and tech startups. The applications of CNN so far seem more or less out of reach for most people. That's the reason why we decided to focus our efforts on creating a comprehensive course with a focus on deep neural networks. That's a great value you can add to any company you work for, which CNNs don't really deliver as they have a different focus. Okay, in the next lesson, we will make a quick overview of RNNs. Thanks for watching. While CNNs are great for modeling and dealing with visual data, RNNs, or recurrent neural networks, were specifically designed for sequential data. Examples are trading signals, so stocks, bonds, and forex, or music, where there is a certain flow. Speech recognition and handwriting recognition are also instances of RNNs, as each consequent word often depends on what you said before. It is probable that the suggestive keyboard on your phone was developed through an RNN. Similar to CNNs, RNNs are an extension on top of the NNs we have seen so far. The specific feature of RNNs is that they have memory. Let's illustrate. We have an input layer, a hidden layer, and an output layer. We forward propagate, but we keep the information from the hidden layer. For the second sample, we forward propagate again, but the hidden layer this time is a function of both the input layer, the updated weights, and the hidden layer from the previous iteration. If we want to design a similar figure to that of deep neural networks, we would have the same picture as before, but this time there are additional weights that lead from the hidden units to themselves. Essentially, these are connections between the hidden units and their own values for the previous inputs. By now, every input target pair was independent. With this new structure, an output is formed by the current input and the hidden units' values from previous forward propagations. Therefore, we must learn their weights as well. If you think about an RNN, you realize that it's basically a deep neural network. The net, though, is not just deep, but extremely deep. This is called unrolling the RNN. If we unroll the added time dependencies, we will end up with a deep feed-forward neural network. While RNNs seem very easy following this short description, they are computationally expensive as they are extremely deep. Moreover, due to the high number of layers involved and their interconnection over time, one must have a very focused approach and a solid understanding of deep NNs before diving into RNNs. Alright, well, I'm sure that you now have a much better idea of what comes next, right? After exploring CNNs and RNNs, it is time to tell you that there are scientific papers combining CNN and RNN networks. But that's an issue to be explored in the future, as it is not well established how the two can work well together. In the next lesson, we will conclude by saying a few words about non-neural network machine learning. Thanks for watching! In order to keep our word, we must give a quick overview of non-neural networks machine learning algorithms, just so you have an idea of their existence. Throughout the whole course, we considered discriminative models. A discriminative model is one that uses an input and then provides a probability of whether an output is correct. Another instance of discriminative models are random forests. They are based on decision trees, and this is why they are called forests. The main idea is that decision trees are not so good at classifying, as they tend to overfit a lot. A random forest takes many decision trees and makes the point that many bad classifiers equal a good classifier. And that said, random forests are mainly used for classification. Okay, there are also generative models that don't give an output y given x. The target is actually the join probability distribution of x and y, which carries more information. It goes from inputs to outputs, and then from outputs to inputs. That's useful for problems such as translations. If you have an English to Mandarin translator, you'll probably want it to work from Mandarin to English as well. Or at least, you are going to check if it's working. Without going into detail, examples are hidden Markov models. Hidden Markov models assume that the problem at hand is a Markov process. Broadly speaking, this implies we can predict the future based on the present, just as well as if we had the whole history of the process. That, in a way, is opposite to what we've done so far. Then we have Bayesian networks. As everything that has the Bayes name in it, these models take into account prior probabilities. The difference between a neural network and a Bayesian network is that with Bayesian networks, probabilities of an event occurring are used as the model's inputs. In a neural network, each input alone doesn't mean much, but a model trained on many inputs gives amazing insights. Bayesian networks are quite useful when we have some uncertainty. For example, in medicine, a person may have a certain disease with some symptoms manifested, while another may have the same disease but with completely different symptoms manifested. This is a situation where we have conflicting information. A neural network would be confused, as there would be no trend to be found between the two patients, while a Bayesian network would assume that such a case is not unusual. That said, researchers create neural networks that are designed to reflect such problems with considerable success. We believe this was a good overview of what else we have out there. Neural networks are a great place to start exploring the machine learning universe. Moreover, it seems like they are advancing at a much faster pace than other types of machine learning. It's worth saying that they are so fascinatingly good at predicting that we humans are not quite sure why they beat every other type of analysis we've invented so far. Research is making way, but so far, no one truly knows why these structures solve problems with such high accuracy. However, not being able to understand them completely doesn't mean we can't assess them. And the verdict is 10 out of 10. This course was a great journey, and thus, we'd like to finish with some food for thought. Each problem, no matter if an image, a business problem, or a Shakespeare sonnet, tells a story. With the right tools, you can reveal it and take advantage of it. Now that you have completed this course, you have acquired some very valuable tools, and it's up to you to find and tell the right story.